morning, everyone. Welcome back. This is already day 4 of our winter school, which is a series of lectures on safety and beneficial properties of fermented food products. Today, the theme of the day is mostly probiotics. So we're going to have several talks related to probiotics. And the first talk is going to be on probiotics and their antimicrobial effect. That's going to be done by Professor Ramon S. Rocha. Ramon, I'm almost trying to say Ramon in English, but it sounds weird. So Ramon is a specialist in food safety, management, and nutritional quality by the Federal Institute of Rio de Janeiro, where he also got his master's degree in food science and technology in the Department of Food. He has a PhD on technological processing of animal origin products from the Department of Food Technology, a postdoctoral fellowship in the Faculty of Animal Sciences and Food Engineering, Department of Food Engineering at University of Sao Paulo, and he's a recent hire from the University of Sao Paulo, so he just started here as a professor as this year. So Ramon, thank you so much for joining us and giving this talk. So the floor is yours.
Okay, thank you, Uelinton, to introduce me. Let me share my screen.
Sure. I'll stay with you until the slides are ready and up and running.
You can see my slides?
Yes, just not in full screen yet.
Okay, just 1 minute. Now it's okay?
Yes, perfect. Do you want to go just one forward to see that everything is fine?
One moment, please. Can you hear me?
Yes, we can.
Yes? Okay. And my screen's okay too?
So far, yes. It's in full screen mode. Perfect. You are good to go.
Okay. Can I start it?
Yes, you can. Thank you.
So first of all, I want to thank you the invitation. So thank you, Professor Uelinton and Professor Slav, to invite me. So it's a big pleasure to be as a speaker in this winter school and have the possibility to share some knowledge regarding the probiotics. And also, thank you for everyone to coming up in this morning. So the title of my lecture is the probiotics and their antimicrobial effect. So here is a brief summary of my presentation. So in the first part, I will talk about the history of the probiotic and also their definitions and advantage of the probiotic for the human health and consequently their beneficials in food products. In the second part, I will talk about the food applications and the main act of the probiotics against the important pathogens in foodstuffs. And consequently, what is the mechanisms inhibitory of the probiotics provides against these important pathogens. And the last one, in the final part of my presentation, I will talk about some trends and I bring it for you some papers. So before I start, I want to briefly introduce me. So as Uelinton said, I'm from the University of Sao Paulo that I recently joined as a professor. So our university is located in the state of Sao Paulo, in the Faculty of Pharmaceutical Science. As you can see, our position is exactly inside this yellow circle. And as you can see in this picture is a beautiful and big campus. So if you want to visit us, it will be a pleasure and I will appreciate that. Okay, now to begin a little of history. So the concept of the probiotic originated in the early of the 20th century when Eli Metchnikov, this man in the picture, suggested a fermented milk product to positively impact health. So he was a researcher of the Pasteur Institute, and people call him a father of the immunology. And also, one of the first evidence of the antimicrobial effect was suggested by Dordalen, who proposed the lactic acid fermentation to confer resistance to vaginal bacteria against pathogens. So, several researchers have indicated the consumption of fermented foods containing probiotic strength to benefit the health through the alteration of the gut microbiota. And these factors, accompanied by the major advantage in functional foods, reaching the research and increased consumers' awareness has accelerated the popularity of the probiotics in recent times. So this is a interesting figure because it's the global market forecast regarding the probiotics as well. And as you can see, for example, in the last year, in 2023, we have around $66 billion of the probiotics in worldwide. And when you compare, for example, with this year, in 2024, we have here a little increase, and we stay exactly in $71.2 billion. So look at what is very interesting because the forecast for 2029, it's a considerable increase in these numbers, and it's reaching above than $100 billion. And regarding the continents, we see, for example, that the Asia was the most responsible for these numbers, and followed by Europe and North America. Okay, and I imagine that we can have many graduated students, and I hope yes, or even people that don't necessarily know exactly what probiotic means. And someone can question, okay, professor, but what is the probiotic? So it's a complex question to answer in the truth because nowadays we have the many definitions of probiotics worldwide. So one of the most famous and the most used concepts of probiotics, as you can see, for example, in many papers or book chapters, is live microorganisms which, when administered in adequate doses, confer a health benefit on the host. So I want to highlight two important parts of these definitions. And the first of them is alive microorganisms. So it's important to mention, to have in mind that probiotic, it's not a compound, it's not an ingredient in food compositions. So probiotic is alive organisms. So it's an important factor to have in mind. At the same time, it's a big challenge for the food industry. And the second one that I want to highlight for you is administered in adequate doses. So to be considered a probiotic product, a probiotic foods, we have probiotics have to be present in higher concentrations during all periods of the shelf life of this product. And normally, these doses is above than 6 logs. Okay, now we know what probiotic is, but who is the probiotics? As you can see here in these screens, I bring very names of different microorganisms, and I want to highlight first of these two genus, the Lactobacillus and Bifidobacterium. So these two genus was the most famous probiotics and the most used probiotics in food formulations. Inside this genus, we can have many species. For example, the Lactobacillus acidophilus, Plantarium, brevis, or even Bifidobacterium bifidum and others. So at the same time that this is the most famous probiotics used in food formulations, they present some difference between them. The first of all, so as you can see here in these figures, regarding the morphology of these two genus, Normally, lactobacillus presents a more uniform shape, while in bifidobacteria, this behavior is not observed. Normally, it's not a regular shapes and not a regular morphology. And despite these two genus be considered the most famous probiotics, we can also have, for example, other microorganisms that can be considered probiotics as well. For example, we can have some yeasts, such as the Saccharomyces boulardii, or also others genus of other bacteria. Now, I want to talk about the advantage of the probiotics. So, as we know, probiotics are able to provide wellness, and at the same time, they can present many health benefits for the host. So, here I list for you the main advantage of the probiotics for health. So the first of them, probiotics can produce lactic acid or even other organic acids, such as lactic acid, for example, that will consequently reduce the pH of the intestine and consequently will inhibit the growth of some pathogens. The second one, probiotics can decrease the production of variety of toxic or carcinogenic metabolites. And the next one, probiotics can aid absorption of minerals, and especially calcium. And probiotics can produce beta-D-galactoside enzymes that break down lactose. And this is an important factor, for example, that people who present the lactose intolerance. And also, probiotics can produce a wide range of antimicrobial substances, for example, bacteriocins, that I will talk more later, and can be a good producers of vitamins, especially B and K vitamins. And the last one, probiotics can act as a barrier to prevent the harmful bacteria from colonizing the intestines. Okay, here in this screen, it's just to summarize, and you can see with more details the benefits of the probiotics for our health. So the first of them is, for example, the action of probiotics in the metabolic effect. So, for example, probiotics can supplement of short-chain fatty acid and vitamins that consequently reduce the risk of factor for colon cancer, and also lower level of toxinogenic or mutagenic reactions in the guts that will reduce the risk of colon cancer either. And also, as I said, probiotics will provide the lactose hydrolysis. This consequently is a good factor to improve the lactose tolerance. And when you see, for example, their action in the immunomodulation, we see that probiotic can alleviate food allergy symptoms in infants. So it's really important to offer probiotic foods, for example, in childhood. At the same time, they can control of the inflammatory bowel diseases. And when we see specific their action in the normalize of intestinal microbiota composition, we see that probiotics is a very important factor to prevent the colonization of some pathogens. Okay, this first part of my presentation is just to introduce probiotics for all of you and just to summarize some aspects. But now in this next part of my lecture, I want to talk about specifically of the application of probiotics in food products. So, as we know, probiotics can be present in many products, in many food products. And here is the source of the probiotic food. So, as you can see, we have mainly two groups that you can find probiotics. So the first of them is the dairy-based. That is the most famous groups to offer probiotics for the human diet. For example, inside this group, we can have soy milk, yogurt, and many kinds of cheeses, or even fermented milks, their desserts and others. And we have recent applications of probiotics, for example, in ice cream, that at the same time it's a big challenge for the industry. And we can also have the non-dairy based products. And inside this group, we have two little groups. For example, the first of them is the vegan. As we can have the cereals and soy, and fruit and vegetables and soy as well. And the other one is the animal-based product. So inside this group, you have the fish and meat products. And here it's an interesting graphical because here we can see, for example, the composition of the microorganisms that are present in these non-dairy based products. For example, we have the cereals, fruit and vegetables, and meat and fishes. And so as we can see here in this first part, we see, for example, that the lactic acid bacteria, represents for the blue color, is the higher present in all these products. So, for example, the second one, we have a mix of cultures that in many times lactic acid bacteria are present in this group too. So we see again the importance of lactic acid bacteria to produce probiotic foods even in non-dairy based fermented products. And we have a little amount, for example, of the yeast, mold, and other fungus with probiotic characteristics. Okay, so the extensive demand of customers for fewer chemically and more natural biopreserving food products have given rise to new areas for intensive research work on antimicrobial compounds produced by probiotics that could effectively battle the pathogens in foodstuffs. So, biopreservation strategy are a method for preserving foods using non-pathogenic safe microorganisms that we can call, for example, of protective cultures that are selected to prevent the development of other undesirable microorganisms. So here in this part, you see to be considered probiotics, the microorganisms has to pass through 5 steps and finally can be considered probiotics that will be applied in a food matrix. So the first of them, obviously, that we can to make the identification of these microorganisms. So we will identification our genus, species, and strains, and we can make this by the phenotypic and genotypic methods. And the second one is the safety assessment. So we can do by the in vitro or animal assay. And normally the second phase is divided in 2 phases. Okay. The next one we have to functional characterization, and again we can make by in vitro or animal assays. And the next is the efficacy and finally the labeling and validation these probiotic microorganisms. And if these can pass through all these steps, they can be considered as a probiotic microorganisms and finally be added in food formulations. So here's just to summarize, we have here, for example, the probiotic food mark ecosystem. So as I said, you can have many strains that can be considered as probiotic. So we have here many bacteria or some yeasts and others. And these probiotics will be act to improve our wellness and to improve the health benefits. So it's important to have in mind that probiotics not necessarily provide only benefit for our health. So in some cases, probiotics can improve the benefits in the product. For example, many fermented products that probiotics can increase the sensory characteristics and consequently the acceptance of these products by the consumers. So finally, probiotics can be added in many food metrics. So as I said before, And we see that the main probiotics foods are represented by the dairy products, but it's not the one. We can have, for example, others food metrics that can be fight probiotics in their formulations. And finally, these probiotics reaching the end consumers. Okay, now we know that probiotics can offer many health benefits. So, for example, inhibitions of carcinogenesis, immunomodulations, or even acting the gut and brain health, for example. But I want to talk about now specifically of the ability of the probiotics to inhibit important pathogens in foodstuff. So, to inhibit the pathogens growth, probiotics can use the inhibitory mechanisms, and these inhibitory mechanisms are a competitive, exclusive competitions for energy, for nutrients, and also the production of inhibitory mechanisms. So competitive exclusion refers that a pathogenic bacteria was directly or indirectly suppressed by introducing at least one of non-pathogenic bacteria in a closed environment with limited nutrients and energy sources. And at the second one, the competition for energy. As you know, the ATP is essential for the microorganisms to maintain a stable intracellular environment through the active transport of hydrogen ions and ions, for example. So, for example, the overproductions of lactic acid bacteria metabolites may generate additional energy expenditure. So, this will inhibit the ability of some pathogens to produce energy. And in addition, probiotics could produce some acids, for example, lactic acid or acetic acid, which eliminated the coupling of ATP and electron transport for inhibit the activity transport of internal proteins, and consequently will lead a reduction of its energy productivity. So, in general, the competition between microorganisms arises when they compete for the same ecological niche. A simple example of this is a production of probiotic fermented milks that the probiotics will consume the lactose that could be an important substrate for some pathogens. And also we have here the production of the inhibitory mechanisms. The first of them is the production of the bacteriocins. So it's very important compounds to inhibit pathogens growth. So bacteriocins are a class of peptides or precursor with the antibacterial, anti-adhesive, or antibiofilm functions that are produced by certain bacteria. And normally they are a low molecular, thermostable, antimicrobial, and also can be produced, as I said, for many species of the lactic acid bacteria. They are shown the antimicrobial activity against food pathogenic bacteria and certain types of fungal species. So bacteriocins can kill or inhibit the bacteria strains that are related or unrelated to the bacteria that produce them. However, in general, it will not harm the bacteria that produce them, because such bacteria usually synthesize self-immunity proteins that are protected them from being killed by their own bacteriocins. So here is just to summarize and just to resume the actions of the bacteriocins in the foodstuff. It's important to mention that bacteriocins can stay present in the foods in two ways. The first of them is the use of the isolation bacteriocins. So they have to pass through many process, for example, purification and isolation, and after them they will be applied in the food formulations. And the next way is the production of the bacteriocin inside the product by the own microorganisms during the fermentation process. So in both situations, bacteriocins can act as antimicrobial agents or even the preservative agents. In these two situations, they will be applied in the foods. So as you can see, bacteriocins can act in many food metrics, for example, in cereal, fruit, vegetables, dairy, and meat and fish products, and also act against the most important pathogens in foodstuffs, as you can see here inside these boxes. And finally, consequently, bacteriocins will reaching a food preservation, and it's an important factor for a food safety as well. Here is the one of the mechanisms that the bacteriocins can act against some pathogens. In this example is the action of the bacteriocins against Listeria. So some bacteriocins can accumulate it on the bacteria cell membranes and exert antibacterial functions by targeting a bacteria cell membranes. So in the left figure, as you can see here, bacteriocins can inhibit the lipid 2 on the cell surface, okay, and dairy B will eliminating the peptidoglycan synthesis. And the second one, in the right figure, bacteriocins can inhibit or kill the pathogens by binding to the mannose phosphorinterferase system, and consequently will form a pore in this membrane. Okay, here is some examples of the using of the action of the bacteriocins. So we can see, for example, the carbamazepine that can have an action against the Listeria. We have another one is the maltaricin CPN that is a strong activity against gram-positive bacteria, mainly Listeria, but no effect against the gram-negative bacteria. And the two last, we have, for example, the plantaricin GI22, and plantaricin LPL1. And in these both situations, they present activity against foodborne spoilage bacteria and pathogens, for example, against Bacillus cereus. And these bacteriocins can be synthesized or produced by the Lactobacillus plantarum. Okay, the second inhibitory compounds that bacteriocins can produce are the organic acids. So organic acids produced by probiotics have been proven to have a strong inhibitory effect against pathogens. So probiotics can produce organic acids, for example, lactic acid, acetic acid, or propionics as well, and via the metabolic fermentations of carbohydrate. And some of these organic acids form an acid environment and slow down the growth rates of the pathogens. So here in this figure, we can see the antimicrobial mechanisms of the organic acid against these microorganisms. And the first of all, we have, for example, the organic acid dissociated into hydrogen ions and acid ions in the cell, and consequently leads to an increase in intracellular osmolarity. The next, we see that that organic acid can destroy the outer membrane and consequently lead the intracellular substance to leak. Okay. The next one, organic acid affect the synthesis of DNA and the translation process of proteins. And finally, hydrogen ions and acid ions generated by the dissociation of organic acids in the cell cannot diffuse out of the cell by the free diffusion, and the pathogens requires additional consumption of energy, ATP, which consequently reduce the efficiency of the bacteria productivity. And we have other inhibitory compounds. So many probiotics could produce the EPS. Sorry, but I forget exactly the pronunciation in English, but in Portuguese is exopolysaccharidio. So the EPS produced by lactic acid bacteria has been reported that to limit the initial attachment and self-aggregation, reduce the mutual modification of cell surface, and inhibit the biofilm formation, for example, against Listeria monocytogenes. And probiotics can be an important Chias inhibitor. For example, so the Chias is an important process for intracellular communications in biofilms and occurs mainly during the initial aggregation phase of biofilm formation, and also in some cases inhibited the virulence. So, as you know, probiotics have a strong activity against bacteria, but not necessarily only against bacteria. So probiotics can act against fungal pathogens as well. And here we can see the most important pathogens, fungals that you can find in foodstuff. And the way that probiotics act against the fungals, in some situations, it's very similar when we compare to the action against the bacteria, but obviously that we have some difference. So as you can see, probiotics can act in the competitive exclusion. For example, the competition with fungal pathogens for nutrients, secretion of antimicrobial compounds, as I said before. And this is an important factor. For example, probiotics can make a degradation of fungal toxin. And also act in the immunomodulations, for example, the production of the anti-inflammatory factors. Okay, here is the first papers that I bring to you. These authors tested the inhibitory effect of the Lactobacillus plantarum and Lactococcus lactis against the Listeria monocytogenes in a cheese model. And as you can see here in the left figure, it's related the action of the Lactobacillus plantarum against the Listeria monocytogenes. And the right figure is related the action of the Lactococcus lactis against the same pathogens. So as you can see, the growth of the Listeria in a control sample increased from about 5 to 7 log within 24 hours, reaching about 9 logs after 7 days of storage at 10 degrees. So it's an expected result because don't have nothing to inhibit the growth. When Listeria was added together with the lab strains, different strains in the growth were obtained and difference in the degree inhibition were noted among the strains. So in general, all probiotic strains that determine the Listeria log reductions numbers with respect to the control, ranging from 1.48 to 4.16 for Lactococcus and 1.96 to 4.21 for Lactobacillus. So 3 strains were able to significantly reduce the Listeria counts by about 4 log units compared to the control cheese, and by 1.5 logs units compared to the initial inoculum at 7 days of storage. So other Lactobacillus strains, as you can see in gray, yellow, and light blue bar, show a good bacteriostatic activity with a reduction of more than 3 log units compared to the control. And after then, the unexpectedly low anti-Listeria with the strain 6LS5, as you can see in light green bar, could indication the presence of the bacteriocin adsorption on the cell surface on milk proteins, or even a low bacteriocin production in situ. So it has been shown that some factors related to the cheese composition can affect the effectiveness of these bacteriocins. The next study, so the next paper that I want to show, investigated the assessment of the bioprotective potential of lactic acid bacteria against Listeria on a cold smoked salmon storage at 8 degrees. So this study used 2 bacteriocins like Produtos that were isolated from smoked salmon, identified as Lactobacillus curvators and Caernobacteria maltomaromaticum, and a recognized bioprotective bacteriocin produced from meat origin, Lactobacillus psyche and CTC494. And the authors used 3 smoked salmon types with different physicochemical composition, mainly fat, mustard, and phenol, and acetic acid concept. And as you see here in this table, Lactobacillus sakei inhibit the growth of Listeria monocytogenes after 21 days of storage at 8 degrees in all the products tested, while in the Lactobacillus curvators only limited the growth of the pathogens, so a little less than 2 logs, as you can see here. Okay, here is just to summarize. For example, the Lactobacillus CTC 494 provide the bacteriostatic activity, demonstrate the best anti-Listeria results, and followed by Lactobacillus curvatus. And the results of the cyanobacteria, for example, were similar to the control sample with no significant difference. Okay, they conclude that probiotic can inhibit Listeria colonization, but never eliminated them. So combinations of probiotics and other antibacterial substances could be a possible solution to further control the growth, violence, and biofilm formation of the Listeria. For example, some studies have reported the use of the probiotic with prebiotics, such as FOS, as example, that we are able to reduce the growth rate, adhesion ability, and invasion performance, and wireless gene expression level of Listeria. This next paper, the authors investigated the probiotic properties of the Lactobacillus casei and Lactobacillus plantarum against the Salmonella paratidae. First of all, they evaluated the probiotics attributes, for example, the biotolerance and the pH tolerance, and also the antibiotic testing and auto aggregation as well. So here we see, first of all, the authors tested 120 lactic bacteria that were isolated from different traditional fermented foods, and that all only 12 strains were selected based on their antimicrobial activity. So the isolated were able to ferment all sugars tested with the acid production and showing the optimum growth at 37 degrees after 24 hours of incubation. So they conclude that 27 degrees is the better temperature for the probiotic growth, and in the end, Lactobacillus casei 100H, as you can see here in the left, and the Lactobacillus plantarum 71 in the right column, presents the better results compared to the other strains and proves their potentials probiotics. So as you can see here in this table, for example, in an assay regarding the growth at different temperatures, we see that most of them are able to increase, for example, in 37 degrees, above than 60 to 17%. And we talking about, for example, the growth at different pH, it's a very interesting result, because we see, for example, that all of these strains are able to grow in many ranges of the pH values. For example, above than 17% in all these situations. And they also made carbohydrate fermentation tests and the antibiotics too. Okay, here you can see in these graphics the survival rate conditions, in different conditions, survival rate, that they use it for tested, for example, the growth of the Lactobacillus casei and the Lactobacillus plantarum. The first of them is the survivor under the 0.3% of the beach salt conditions. And as you can see in the beginning of the experiment, they have counts above, I think, 70%-ish, and this presents a little decrease during the incubation times after 5 hours, as you can see for the both probiotics. And when you see specifically in the pH 4 and pH 2 conditions of the survival rate, we see that in the beginning of this assay, all these probiotics present survival rates above than 80%. But when we have when the incubation times pass, we see that these probiotics present quickly decrease in their viability. So this behavior can be observed in all these situations for all tested that they were made. It's an important result because you can see the lactobacillus and salmonella co-culture experiments. So as you can see, lactobacillus casei and lactobacillus plantarum significantly reduce the growth of the salmonella at the 37 degrees. And regarding the biofilm inhibition assay, it's an interesting result as well, because you can see that the lactobacillus plantarum can reduce above 18% of the biofilm formation, while in the lactobacillus casei, 75%. That is a good result either. So the antimicrobial activity of this probiotic against the important pathogens that we can find in foodstuff. So as you can see, we have the E. coli and Klebsiella, Staphylococcus, Pseudomonas, and finally Salmonella paratifi. As you can see, in the middle concentration, in all of the situation of the concentration of the 15% are able to reduce the growth of all these pathogens above than 18%. So it's a really important result. So when you see specifically for two results, for example, against the E. coli and Klebsiella, we see that the lower concentration of 10% don't have a good result when compared than the others concentration. Another important result that I want to highlight is the action against Pseudomonas and Salmonella paratifi. So that we see that the lower concentration of the lactobacillus casei, it's not able to provide a significantly reduce of the growth of these both pathogens, while in the lactobacillus plantarum, the lower concentration provide interesting results above than 80%, for example. So here is the salmonella evaluation of the anti-salmonella attributes. So in vitro time kill assay evaluated the cell count reductions of the salmonella in the presence of these two probiotics. And as you can see, we have here the lactobacillus plantarum completely inhibit the pathogens after this time of incubation, while in the lactobacillus casei, they inhibit the salmonella growth after 24 hours of incubations. And when compared, for example, with the headline, that is the control sample with no probiotic added, we see that has a big difference between the treatments. Okay, here we can see the figure regarding the scanning electron microscopy of the formation of the biofilm formation. We can see the middle figure and the right figure is the biofilm formation with the presence of the lactobacillus casei and the lactobacillus plantarum. So we can see that the presence of these two probiotics provide not uniform and not well-developed structure of this biofilm, while in the control sample we have, for example, uniform and well-developed biofilms. Okay, and the authors also tested the antifungal activity of these two probiotics, and the authors tested for antifungal activity against 80 antifungal species, as you can see here in this table. And as you can see, the lab isolated of the lactobacillus plantarum showed the high zone of inhibition against practically all of these fungals, especially for one, okay? And while the isolated of the lactobacillus casei had no inhibitory effect after 7 days of incubation against all the fungals tested. And here it's interesting pictures, as you can see in the first line, for example, we have the action of the Lactobacillus casei against these all fungals. And as you can see, Lactobacillus casei had no inhibitory effect. So they not able to provide any precipitation halo when compared, for example, for the Lactobacillus plantarum, that can be able to provide the precipitation halo in the inhibition zone in practically all of these treatments, as you can see here in this plate. So now I want to share with you some new approaches regarding the use of the probiotics in food system. As you can see, this recent review that addressed the probiotics incorporation in edible packaging. Okay, as we know, the food preservation is a vital step in the food process industry to prevent the rancidity of flavor, oxidation, changing in tastes, micro spoilage, loss of feminine emulsions, color, texture, and nutrients, for example. So to prevent these questions, we have the traditional conservation methods, such as refrigeration, modified atmospheric packagings, radiation, sterilization, and pasteurization. But in some cases, these methods can be unsuitable for some kinds of foods. And so edible packages has been used in recent years to extend the shelf life and improving the nutritional values of foods. Okay, edible packaging might act as a possible substitute for supplying and carrying probiotics to food products. And as you can see here in this figure, the action of the probiotics in edible packaging, and sometimes it's very similar when we compare to the action of the probiotics inside the food matrix. For example, probiotics can synthesis of hydrogen peroxides. They can eliminate pathogens by the competitive inhibitions, and also synthesis of antimicrobial peptides, for example, bacteriocins, as I said, and also production of organic acids. So we see that the mechanisms also be similar when you compare to the action inside the food product. And this consequently will reach in the extended shelf life of the product and improve the food safety. And here is some examples that you can find in the literature of the use of probiotic in edible packaging. In the first line, you can see, for example, the presence of the Lactobacillus acidophilus that act against the fungal and aerobic mesophil bacteria. And its important results is they present counts above than 7 logs after 90 days of storage at 4 degrees. So this last paper that I want to discuss with you, this study demonstrated the ability of the specific strains of the bacillus to promote food quality and safety. A true probiotic bacteria is related many times for lactic acid bacteria. It's important to mention and important to have in mind that we can have all these bacteria with the probiotic potential. For example, some strains of bacillus. And while Bacillus cereus is considered a food pathogen due to the potential to cause foodborne, some subspecies and strains have been identified as safe and beneficial probiotics under specific regulatory frameworks. These specific strains can act in immunomodulation, anti-cancer effect, cholesterol reduction, vitamin production, and obviously the ability to produce antimicrobial substance. So just remember, to be considered probiotic, the microbial strains had to be provide beneficial effects on the host, and also increase the growth of disease resistance, be non-pathogenic and not toxic, obviously, and be viable in a large number in the final products, and be able to survive and metabolize in the gut environment, and finally show the stability in the storage and the field conditions. So this is my email. And if you have any doubts, please feel free to contact me, or even to discuss some products, some projects. And thank you for your attention.
Can you hear me? I don't think. Hi. Can you hear me, Ramon?
Yes,
Can you hear the moderator?
I don't think. Som. Ah, mas aqui tá saindo. Can you hear me, Ramon? Oh, great. Thank you so much for the talk. Very rich, and with lots of ideas for new studies, as I was talking to some of my students as well. We have a question from the chat. I'm going to read that to you, and then we can also take questions here. I'm sure Slavi will have lots of questions. So one question is by Ícaro Oliveira. What are your insights on how probiotics interact with native microbiota in the gut? Are there specific conditions or factors that might lead probiotics to outcompete beneficial native microbiota?
Sorry, can you repeat, please? I think it can be better in Portuguese because the audio is not so good, and in English, I think there will be most difficult.
Sorry. I'll ask the guys to also put the question in the video, so maybe you can also read it. But the question is in English, so yeah, what are your insights on how probiotics interact with the native microbiota in the gut? So are there specific conditions or factors that might lead probiotics to outcompete beneficial native microbiota?
Okay, thanks, Ícaro, for your question. Can I answer in Portuguese or in English? What do you prefer?
I think in English, because we have people that don't speak Portuguese in the audience.
So we have the main ways that probiotics can interact, for example, with the native microbiota in the guts. As we know, as I showed during my lecture, we see that probiotics can provide different actions against these pathogens. For example, the competitive for nutrients and competitive for energy as well. And this consequently will reduce the growth and the colonization of these pathogens in the gut. And this behavior can be observed also in the food metrics, for example. The next one, specific conditions, and I think that is it. So we have the many ways that that probiotics can act against these pathogens, and I think that I can answer your question.
Thank you. I think like what Ícaro is bringing is a little bit different. Like we don't usually think about the probiotic acting against the native beneficial microbes, but we only think about probiotics against the pathogens. So it's asking against the beneficial native microbiota. I don't know if anyone has done that.
Let me try to answer. So as I said, for example, when we're talking about the bacteriocins, as I said, some bacteria can produce immunity against the other bacteriocins. And in some situations, for example, if I have beneficial microorganisms, they not necessarily will be deaf for our own bacteriocins because they can produce some proteins that will defend them of these actions. And consequently, they will be providing more specific action against only for the pathogens bacteria in some situations, of course. But we have to see specifically in all situations to have to know the better conditions for these situations and for these actions.
Sure, thank you. We only have time for one question, so I'll ask, Slavi will ask the question.
Actually, my question is related to the fact that you mentioned one example when they was doing a biopreservation with using biopreservative culture. at 8 degrees Celsius. However, we know very well that most of the lactic acid bacteria, they cannot grow at below 15. In fact, some enterococci maybe, but not really below at this temperature. So how we can actually, what's your suggestion, what's your idea, how the bioprotective culture actually acting when we're in the refrigeration condition and they do their job, and in fact they cannot even, some of them cannot even survive. Well, at least they maybe survive, but they cannot grow. And if they don't grow, they cannot express the antimicrobials. So what's the potential mechanism that we may be supposed to link to this observed condition?
Okay, thank you, Slav, for your question. And my audio is not so good, but I try to understand. So, first of all, the important strategy that we can make is, for example, the use of the microencapsulation of the probiotics. So this can reaching the better survival of probiotics during the shelf life of the products, or even, for example, in edible packaging. So I believe that the microencapsulation can be a good strategy to make this, to improve this characteristic of the probiotics and leading their survival during the shelf life. Sorry if this is not a question, but the audio is not so good for me.
No, we can discuss this later. I think we don't have time for discussion now because the next presenter is almost knocking on the door and asking where you're going to start. So,
Okay.
Uelinton?
Yes. Ramon, thank you very much for your talk. It's a lot of work to put on a talk like that, so I thank you so much for that. And we continue our program now with, I was using the wrong mouse here. Yeah, with Professor Mike Chikindas. I'm just going to open his bio here real quick, because the time is really like when you only have 1 minute for 10 o'clock, so I can just keep on going with the program. So Professor Michael Chikindas is from Rutgers University in the US, and he's going to be talking to us about applications of solid-state fermentation processes and bacillus, microbes, biotechnologies, and biorefinery. So Professor Chikindas has a BS and a master's degree in genetics from the Yerevan State University, Armenia, from former Soviet Union. His PhD in microbiology was in the Research Institute of Genetics and Selection of Industrial Microorganisms of the Ministry of Medical and Microbiological Industry, Moscow, Soviet Union, former Soviet Union. Professor Chikindas is a professor of microbiology leading the Health Promoting Naturals Laboratory at Rutgers. He co-authored several patents, more than 100 papers, and several book chapters. He serves on the editorial boards of Applied Environmental Microbiology, Letters in Applied Microbiology, and of Annals of Microbiology and Beneficial Microbes. He was founder of Probiotics and Antimicrobial Proteins Journal, a Springer Nature journal, and serves as its editor-in-chief for 12 consecutive years. So he served. He also served on the editorial board of the Journal of Applied Microbiology for 25 years. He's a member of the American Society for Microbiology in the US and the Society for Applied Microbiology in the UK. So, Chikindas, very nice seeing you again. Thank you so much for participating in our winter school. It was not only the talk, but this is a bigger project, and we visit Chikindas at Rutgers. We spent a very nice week over there, and now he's here talking to us. It's a pity that he cannot be in presence, but at least we have him online. So thank you so much, and the floor is yours.
Good morning, everyone in Sao Paulo. Good day, everyone, whichever place you are now. And it is a great honor and pleasure to be with you. And guys, I really miss you. I miss Sao Paulo, my time there and communicating with the students and with the scientists, and really nice time we've had during your trip to Rutgers. I took some time to watch several presentations from this winter school since the first day, which were conveniently uploaded on YouTube. And I just want to encourage everyone to revisit these presentations whenever you guys have time, because these talks are really fantastic, and I personally learned a lot from them. And I would like also to express my gratitude to the organizers of this winter school for inviting me. It is an honor and pleasure to be with you. Today, I will be talking about microbial valorization of agricultural and food industry waste. And of course, most of the time, I will be talking about probiotics, but at the same time, some other microorganisms of biotechnological importance will be mentioned as well. The outline of my presentation is as follows. I will start with the introduction into the topic. We'll then look briefly into the submerged and solid state fermentation. We'll change the gear. We'll talk about the valorization of fruit and vegetable bio-waste. Then we will zoom into the spore-forming bacilli and the opportunities to use them for valorization of the biological waste that is coming from agricultural and food industry. Finally, we will look at the ways to use biological waste from the mentioned industry, not just as substrate for growth, but also as delivery vehicles for probiotics. And of course, this way, again, we are creating additional value to the substances in question. And finally, we will conclude this talk. Why agricultural and biological waste? Of course, we know that there is a lot of waste produced by agricultural industry and by food industry, but I don't think I'm the only one who never really took a look at the actual numbers, and the numbers are astonishing. We're talking about billions of tons of food that is vanished, billions of tons of the agricultural waste products that are not utilized, are just discarded. And if to look at the fruits and vegetables and other products of agriculture and food importance, we can see 45% of fruits and vegetables, 35% of fish and seafood, 30% of cereal, 20% of dairy products, and 20% of meat are not utilized by the end users for one reason or another. So we're talking about a really big amount of the product substances which must be utilized one way or another. And this utilization should come in a way that is not endangering the environment. So this is a really very big problem and growing problem. So what is the agri-food industrial residue waste, and what it really is falling under the umbrella of these definitions? Uh, Usually, this is the waste that comes from the agriculture, of course, and the food industry production. Um, it's a really broad variety of biologically important products. And the important thing to mention here, and of course for myself not to forget, I highlighted the bold, different color, high value components. And indeed, we have polysaccharides, proteins, fibers, flavors, and many, many other bioactive compounds that are just sitting around us and not being utilized, and they can and should be utilized for a variety of products of importance for humans and animals. And that includes not just food products, not just biologically active additives, but also pharmaceutical, personal care, cosmetic products, and many other areas of application are waiting for these substances to be utilized. When we look at and we're just talking about solid residuals now, all right? So agri-food industrial solid residuals that are readily available for utilization. And again, there is no probably need to even mention all of them, but you can see in agri residues we have stubble, stalks, stems, sour leaves, and everything else. And in the food industry, brands, germ, peel, seeds, skin, and oil cakes, and many other uh, product leftovers of both industries that are readily available for utilization. When we're zooming into the food processing biowaste, and again, food industry, it's not just it's food industries in plural, and we have poultry, meat, fruits and vegetables, brewery, oil production, vegetable processing, and all of these food-related industries produce tremendous amount of waste, which still carries certain value. And this is something that I think creates the justification for our talk. I mentioned that I will be talking about valorization. And quite honestly, when I was trying to find the definition, it was quite a challenge. I didn't expect it to be that much of a challenge. Um, and finally, I came with something, of course, the internet source, but it's the legitimate, reputable source from the Dutch group. This is a very generic definition, but it I feel comfortable with this definition. And basically, the take-home message is that we have something that is seemingly a waste. And it doesn't matter whether it is a waste in agricultural, food industry, or any other area of our activity. All right. And we're utilizing our knowledge, our ability to squeeze something else, something meaningful, something useful from these uh, residues, waste materials, or, otherwise, in quotes, useless things, and we're adding value to these uh, substrate product substances, which create additional benefit to the society at large. And under the umbrella of the society at large, of course, we have human health, animal health, agricultural industry, pharmaceutical, health promoting, etc., applications. All right. Um, Before we move forward, I need to introduce several definitions. And some of things already mentioned before, solid state fermentation, and that is where the microorganisms are growing on the solid materials, submerged in the solids, but literally it's not, dive deep into something like in the case of real submerged fermentation. Real submerged fermentation is where the microorganisms are growing in a real liquid environment. And one more definition, SCPs, single cell proteins. Of course, many of you know it, but still, I feel we need to, excuse me, introduce it. It's proteins, well, derived from single cell type of organism, from yeast, from algae, molds, and bacteria. And these can be useful for a variety of applications in different eukaryotic cells. So now empowered with these definitions, we're looking at the production of bioactive compounds from food industry waste using fermentation processes driven by microorganisms. And again, we have examples here, and of course, not all of the food industries are mentioned here, just some most significant, perhaps ones: meat and poultry, fruits and vegetables, marine, grain, brewery, and we can actually come up with many more, and all of them produce waste which can be utilized, can be further processed through the solid state fermentation or submerged fermentation to produce many biologically valuable substances and materials such as antibiotics, enzymes, single cell proteins, SCPs, biofuel. And I believe there was a talk in this winter school focused on the biofuel, antioxidants, polyphenols, and many, many other substances of great importance for eukaryotic organisms. Now, some of you who know me well really are aware about me being crazy about solid state fermentation, and there are many reasons for that. But being a fanatic of the solid state fermentation, I am not saying that the submerged fermentation should be neglected. And what I give you here is an example of our study, which we conducted in collaboration with the Agricultural University from Tbilisi, Georgia. And what we were looking at is whether all kind of plant raw materials, byproducts, can be further processed with the help, with the assistance of probiotic microorganisms. And in this case, with this example, I give you a Bacillus subclass Tecmira 1933, which is a spore-forming probiotic microorganism reasonably well characterized by us and our coworkers. And we did show that this microorganism is beneficial for poultry. Now there are ongoing experiments showing its beneficial effects in aquaculture. We know about the effect on other eukaryotic hosts. So this is really the microorganism that can do a lot of good things to the eukaryotic host. And why to grow it on some specially designed and perhaps um, scientific media if we can use the byproducts of agricultural or food industry? So what we have here is a variety of these waste materials, such as cheese whey. Okay, I say waste material. Cheese whey, of course, is used and utilized for many purposes. I should probably take my words back a little bit. And mandarin still, all right? Ethanol production residue from the corn, all right? Cottage cheese whey, of course, also utilized also in the food industry, but to some degree, it's the byproduct of the food industry. And what we see here that all of these substrates or media, as they're called in the table, can be used successfully to grow probiotic microorganisms. And what we see in the right column is the number of spores produced. Excuse me, 10 to the 9 spores, so 10 to the 10 spores. So decent number of spores. Why do I emphasize spores, not the cells, not the vegetative cells? And the reason for that is that the way you would prefer to formulate your spore-forming probiotic in the final product is in the spores, not in the vegetative cells. Because in the spores, it will be shelf stable, it will not be subjected to any harmful effects of temperature, moisture, or any other factors that may present themselves in different environments of formulation, transportation, and storage. And again, we can see examples of how these microorganisms is utilizing the mentioned substrate and what we have with regard to the reducing sugar content, what we have with regard to the enzymes produced, such as methylionase or carboxymethylcellulase. And you can see that these are reasonable decent numbers indicating that utilizing the mentioned or other substrates, we may not only achieve decent production of the spore-forming probiotic, but we can also aim at the biotechnological production of certain enzymes and other substances of biological value. Changing the gears and talking about another spore-forming probiotic Bacillus amyloidicefacins B1895, which was passed through the panel of similar tests as the mentioned Tecmira 1933, with the similar results being good in modulating health in poultry, in modulating immune system, in modulating, and I'm trying always to carefully say modulating, not boosting, because often we hear from the students and also from the senior level presenters boosting immune. We don't want to boost immune system. We want to modulate it. All right. So this is a really well characterized probiotic microorganism. And now we're talking about something I personally love, the solid state fermentation, and why I'm particularly in favor of solid state fermentation. And there are quite some reasons for that. It has been shown in the literature that the microorganisms that are produced, the probiotic microorganisms that are produced through the solid state fermentation, are much better surviving the passage through the gastrointestinal tract, number one. And number two, they are becoming active in the eukaryotic host much quicker than the microorganisms, the same actually microorganisms that are produced through the liquid phase fermentation. So I have some reasons to be in favor of the solid state fermentation. So what do we have here? Corn cobs, EPR, mandarin peels. We have some soybeans, sunflower oil meals, wheat bran, wheat straws, and many other things that were tested as byproducts of the agricultural food industry. And again, decent production of the spores, but some of the results I want to particularly bring to your attention, and that is why I have them highlighted in the table. And what we have here, I think it's a decent, interesting take-home message. And again, not a very new take-home message, because many investigators showed similar results in the past for a variety of biotechnological exercises, indicating that it's not only about the number of the cells you are getting in the fermentation when you are aiming at the production of certain biologically important molecules. It's about how the substrate and the conditions of the fermentation favor the production of the certain. So what we see here is 4.9 times 10 to 11, a decent number of the spores, but we have about 10 units per gram production of hyalinase, which is not bad. We have 1.9 with 16.2, but we have 4.7 10 times to 11 spores, and we have 6.6 units of hyalinase per gram, which again confirms my previously made statement that it's not just about the number of the cells you can achieve through the fermentation. It's also about how the conditions, the medium, the environment favor the production of one or another biologically active substance. Changing the gears, going to the next step in in our presentation, fruits and vegetables bio-waste valorization. And this is where I would like to give you an example from the work done by the Chinese group on utilization of the waste of grape production. And I didn't know, to be honest, before I started digging into the literature that the Shanghai area is producing that much of grapes, and that's really a lot. And the big, plantations are readily available there, but the waste of the grape can reach up to 30% of the total production. And then I look at the numbers from other countries, and I must say they're not strikingly different. It depends from place to place, it depends on the methods of cultivation, but it's really big. So, what the investigators put in front of themselves as the research objective. They wanted to evaluate the effect of different inoculate probiotics on the fermentation. They wanted to analyze the probiotics variations and chemical composition of fermented products and to explore the possibilities for applications of these products in the industry. And I put myself here a question mark. I hope you can see because they say probiotic fermentation. When I was reading this paper and I was looking at the results and then at these really very beautifully arranged flowchart, I started thinking, it's really a probiotic. They are using the microorganism to ferment the grape waste, which then goes into the soil, which then benefits the quality of the grape. So it's a kind of a, to me, still pretty much indirect action. And I'm not sure I can really grasp it entirely, whether the effect, and there is a very good pronounced positive effect with the improvement of the amount of vitamin C in the grapes grown on these soil supplemented with a fermented product, in the amount of soluble solid content. And we have almost 17% and 20% respectively improvement as compared to the control, to the negative control. But is this effect solely due to the microorganism or due to the microorganism and the products of fermentation? For the agricultural business, I think it doesn't matter. The effect is really very good. For us as investigators, I hope to see further investigation, further research into this area, showing us what was the contribution of microorganism and what was the contribution of the fermented product to really good positive results observed by these groups. Changing the gears a little bit and now talking about cruciferous byproducts, and this is where we have cabbage, cauliflower, broccoli. And the reason I want to give this example, and this is really a very beautiful paper, quite recent one. The reason I wanted to bring this to your attention is because it is really very informative. And I personally like when the investigators are putting a good effort into creating a strategic picture. And so this is what I would consider a really decent strategic picture. We have the waste generated from these three types of vegetables, different methods of extraction of biomaterials. And the method of extraction is extremely important because certain substances can be extracted using one method but not another method, and certain substances can even be destroyed. For instance, something that is temperature unstable or something that is irreversibly degrading with the increase or decrease of the pH, etc. etc. All right. So then we have different means of bioprocessing, including fermentation. And of course, from that, we have added value products that can be utilized. And here is just a few examples: food industry, pharmaceutical, and biotechnological applications. So again, another example clearly showing us how these waste generating in agricultural production can be utilized for benefit of eukaryotic organisms, that is, including humans and other animals. Different technologies involved in vegetable waste valorization. And again, I'm giving you several examples with cabbage byproducts, broccoli waste, cauliflower waste, and just, some examples to zoom in. And of course, you will have time to look at these tables on YouTube later. But a couple of things that I want to bring to your attention. Uh, you can see, for instance, cabbage byproducts and the production of added value to the silage. Bacillus subtilis involved in the processing, in the fermentation with the improvement of polyphenol content and other substances, hyaluronate production. Of course, we were talking about it earlier, and many other substances. Since bacilli were mentioned already on several occasions, I have no choice but to turn into bacilli, into the spore-forming bacilli, and they're used for valorization. And this is where I would like to turn to another review paper, a recent review paper, which is talking about industrial application of bacilli as a first step towards circular bioeconomy. And this is the kind of a rolling circle picture from the paper I mentioned, and there will be a few tables or extracts rather from the tables of the same review paper. But indeed, what we see here is the utilization of the product derived from fermentation, including bacilli, as the major contributor to the process. Production of probiotics, we already had several examples previously. Contribution to the feed and food with the production of biologically valuable substances. Production of enzymes, production of antibiotics, plant and other organisms promoting substances production, and many other applications. So, some of the examples from this very interesting review paper, and again, you can see a variety of spore-forming bacilli here. For some, we see the species and the strain are identified, and some are identified at the level of the genus, Bacillus species. And again, as always, I want to bring your attention to some positions, although the entire table to me is really very interesting because we have here a variety of substrates that are coming from agricultural and food industry, utilized for fermentation by spore-forming bacilli, for the production of enzymes. And again, similar to the take-home message I made before, uh, production of polycyclic lipase, but the best results were obtained with coconut fiber. Production of protein, the best result was obtained with a wheat sprout. And I will make here again the same take-home message. When, for instance, you want to challenge your group with conducting research on adding value, valorization of bio-waste products, of course, you will run as many microorganisms of biotechnological importance as you have at your hand. And of course, you will need to look meticulously at which exactly substrate will allow you to produce the highest yield of the desired molecule, or which exactly substrate will allow you to produce the highest number of the cells. If your objective is to produce the probiotic for further utilization by humans or other animals. Again, byproducts, again, bacilli. And we're dealing with the same paper, and this is the extract from the table. A variety of agro-industrial waste. We have soybean meal, rice straw, potato waste, and a variety of bacilli with the production of lipopeptides. And we cannot underestimate the importance of these lipopeptides, citrullin, surfactin, fungicin. They're all broadly used for the benefit of our society. Changing gears with another examples, and here we have the again spore forming bacilli, again agro-industrial waste, and the production of probiotic bacteria. All right, so coming to the point of which substrate to choose when you want to produce microorganisms. 10 to the 8, I wouldn't say I'm really that impressed with the B substrates and weight emitting. But when we have 10 to the 9, 10 to the 11 corn stip liquor with bacillus coagulans, and forgive me for saying bacillus coagulans, the name of the species was changed 2 times since what about a couple of years ago. So I'm kind of a conservative, old-fashioned person, but still I'm not saying it's lactobacillus. Uh, it's a bacillus because in the past it had the name of lactobacillus porogenes. All right, but 10 to the 10, 10 to the 11 are decent numbers in the production of the probiotic microorganisms. Another example with value-added products produced from food waste, and again, we're talking about bacilli. Food waste in this case, not agri waste, but the food aid waste. Um, we have soy hull, alpha. Oops, I'm sorry. Hello, hello. Uh-huh. Where did you stop? Uh-huh. Okay, I'm waiting. Mm-hmm. Yeah, but yeah. Well, probably because it's hot. What is? Yeah. Mm. Is it local or is it more massive? Ah, okay. Mm-hmm. All right. Okay. Take care.
Hi. Hi, Mike. Hear me?
Yes, I can hear you.
Yeah, sorry guys. We had a power surge, but the energy has been restored and hopefully it's not going to happen again. If it does, Mike can continue because the system does not depend on our energy. So everything should
Right.
be free from now on. Mike, sorry for that.
No, thank you. Thank you. It's nice to be back again. Where did it happen? I think we were on the slide, and I guess we kind of finished with it, and we can move to the next one. And here we're pretty much at the last, before the conclusion chapter. I have to turn off my air conditioning. Anyway, I'm getting cold here. Okay, bio-waste and delivery vehicles for probiotics, and of course, at its value. All right, and this is where I will be giving you some examples of the work done by my good friends and colleagues and by us in collaboration with other groups. And I will start with the work that was done by Dr. MinTze Liong and co-workers. And they studied several lactic acid bacteria probiotics and different substrates from agro-waste, looking at the possibility to grow microorganisms on these substrates. And this slide gives you an extract from many, many data that the group published. Um, Three substrates, durian, Symphylac, and mangosteen. You can see the Latin names of the plants next to the colloquial names. And we have these substrates, and that's the electron microphotograph. Two columns, the left column, the substrates on their own, and the right columns are the substrates with Lactobacillus acidophilus FTDC 1331 grown on the substrate. And the last one, I just took it as an example, uh, zoomed into it, and you can see the magnified, even more magnified picture telling you uh, one thing. Yes, they can grow on the substrate. Yes, they're very happy. Yes, they're forming biofilms. And indeed, these immobilized probiotics or probiotic biofilms, they were reported by the investigators as having improved growth, greater production of sucrose, tachyose, and glucose, and high production, reduction and high production of lactic and acetic acids, and these utilization of sugars and production of acid, high production of acid are indicators of the better or more active metabolism of the microorganisms. And of course, these were compared with the non-immobilized cells growing in different substrates. So take home message, the biofilm associated cells, if I can say so, happier, more energetic, and more metabolically active. While looking at the study by the same group, but a different study. Again, we have the report from the group of Dr. MinTze Liong. And I think this study is very interesting because what they did first, as many of us were doing, just looking at the possibility to utilize different agri waste or food waste substrates to grow probiotic microorganisms that they want to uh, produce biotechnologically using these waste as a substrate. Next step is really a very intelligent, clever step forward in the design. So what if this biological waste is used as a primary substrate? And what if it can be enhanced, improved with additional materials that are also coming from the waste, or in fact, they may not necessarily be coming from the waste. So you have a two-component, or perhaps even a multi-component system, which is used not only as a growth substrate, but also as a delivery vehicle in these cases. So we have soy protein isolate tablets STI, which is the foundation substrate for the growth. But then we have banana peel, or we have banana pulp added to these kind of formulation. And what we see is that the cells are more stable on the surface. The cells are less released into the environment. The cells still continue to be metabolically active. So we're really talking about a sophisticated biotechnological process where immobilized on the surface cells are used to produce desired substances. And I think this is a really fascinating, very interesting research, which takes a step forward in understanding of how the bio-waste substrate can be utilized not in a primitive, but also in a very intelligent manner. Whatever is left from soybean, they still grow. And the soybeans themselves and the byproducts of soybeans were mentioned today, if not vocally, then in the tables that I showed you, that I shared with you. And this study came from my trip to China. Some point I was taken by my colleagues in Guangzhou to the local production, and they're using soybeans as a commodity and squeezing literally everything possible from these soybeans. And that's the sauce, the food colorants, the flavors, the pretty much everything. And what we have just cellulose fibers left. And walking in the rooms and seeing big jute bags with these fiber, I asked the guys, "What are you doing with it?" And they said, "Oh, we're doing it pretty much nothing. We're using it as a filler for the animal feed." So literally pretty much nothing. And I said to myself, okay, these performing bacilli, they grow literally on anything, and we should give it a try. And sure enough, the Bacillus subtilis, one of the strains we have here example in electron microphotograph, Katmira 1933, the microorganism I already introduced to you as a potent probiotic microorganism, growing really well on the surface and in many caves of the cellulose, sitting tightly as a biofilm. And through these process of growth at a certain period of time, we can see that the majority of cells will convert into the spores. All right. So even the byproduct of soy industry, such as cellulose fibers, can still be used to add some value to valorize by growing probiotic microorganisms on it. Excuse me, changing it just for the last time. I'm going to talk again about my beloved bacilli and introducing another player to the table, duckweed. Why is duckweed? Sorry, slides are jumping. Why duckweed? And everybody knows duckweed. It's really a weed. Well, in some countries there are more duckweed grow, in some countries less, but it's pretty much all over the world. Known culture used by plant molecular biologists and scientists in general to study as the convenient model to do a lot of various experiments on the plants. But the important thing, well, it's also used actually as the feed for the water birds, if I'm not mistaken. But what is important about duckweed is that it's nutritionally a very valuable type of plant. 20 to 40% of protein, 2 to 9% of fat, up to 30% of fiber, and up to 40% of high carbohydrates is the content of these tiny little plants. And quite a few studies reported on the safety, of course, and the nutritional value of duckweed for humans and other animals. Now, when I looked at this plant at the duckweed and I wanted to study it, some of my colleagues said, well, nothing will happen. And they were having some reasons for saying this. Well, number one, the surface of duckweed is very hydrophobic. Number two, duckweed is producing quite a lot of very potent antimicrobial substances of different natures and different mechanisms of action. But I said to myself, okay, but what if we will pre-treat duckweed? And certain way pre-treated duckweed turned to be a really nice substrate for the growth of, and again, we have here Catmira 1933 and B1895, two of my spore-forming probiotic microorganisms. Three types of substrate for you. Who are the plants, and one was the powder product, which is commercially available as a dietary supplement for humans. While two plants I was able to buy, I don't remember, eBay, Etsy, whatever, some store, internet store at the low price, but these products for the human consumption turned to be quite pricey, and I, just paid out of my pocket to see if the microorganisms can grow on it. Well, what we see here, we can achieve up to 10 to 11 of Catmira, a little bit less, 10 to the 10 of B1895 with L minor, as Polyrhiza is lower, but still decent numbers, and the human targeted nutritional product, not that impressive growth of the microorganisms, but I don't really care that much. Take home message, duckweed. In many places, duckweed is really a weed. We can use it, can harvest it, we can utilize it for the production of probiotic microorganisms and then bring back to agricultural industry, for instance, to feed animals or the same water birds I mentioned before. And when we look at how the microorganism perform on the surface, we have two examples, B1895 at the top and Catmira 1933 at the bottom. Left column is just the surface, and right column is the surface populated with the microorganisms. And again, we can see the cells are happy, the cells are forming biofilms, and after the extended period time of growth, most of them are entering through the sporulation into the spore phase, and that means that they can survive as spores in a variety of products. And we're coming to the conclusion of our today's gathering with me. So, negative and positive issues. And again, this is from the recent publication. I modified the table, extracted what I think is important. I wouldn't call all of them negative, such as the environmental impact, because we still don't know whether this impact is entirely negative. But this is something that needs to be investigated. We know about the possible negative or neutral impact of bio-waste from agri and food industry. But what if these substrates are further processed by microorganisms? Will they become safer, or will these microorganisms generate something that potentially can be hazardous, unhealthy for the environment? We don't know. Standardized protocols for extraction. they are needed, not just standardized protocols, but the standardization of the substrates are very important for the industry if we want to have reliable materials that will be considered by the microorganisms as the growth media, the growth substrate. All right. And of course, operational cost is important and many other things as well. So, finalizing, I'm giving you a kind of a strategic look, a strategic flow chart for the second life of biowaste. And that's something Dr. Orff and I are working on. We have 3 columns: challenges, valorization, and application. Safety effect is something that we always must start with. Selection of biomarkers, essential biomarkers that will allow us to consider one or another type of substrate for further utilization. Standardization of all the processes and profitability. A valorization, what do we expect to achieve here? Sources of bioactive, and it's kind of a generic term, but I wanted to put it as an umbrella for everything else. Sources of prebiotics, uh, substrates for SSF, um, probiotic protectants, and many other issues that can be considered as valorization. And of course, applications come in agricultural, human health, um, domestic animals, and improvement of environment. And with that, I would like to finish my conversation with you today, and thank you for your attention.
Thank you very much, Mike. Do we have questions? We don't have too much time. We don't have too much time for questions, but at least one we could entertain. No questions?
Mike, can I ask you a question?
Sure.
Can you hear Suvorov? Yeah.
And you know that I'm very bad at asking the questions. What's your opinion? In fact, a lot of people talking about when you use the bacillus as a probiotic, and always pointing on the fact that as spore forming, so we can keep the as a spores, transport them, keeping them, everything is okay. But when would they go in the gastrointestinal tract, they have enough time to get as normal vegetative cells. So what the challenges, in fact, when we use the bacillus? Because everyone talking about the benefits, but we have challenges as well. Can you comment
Okay.
on this point?
Yes, I can. And actually, the studies were done by several groups, and one of the groups did actually a very interesting study on poultry. What they did, they were feeding birds with the spores of Bacillus subtilis and retracting, the microorganisms during the passage through the gastrointestinal tract at different stages. And what these investigators found that the spores have time to germinate, multiply in numbers, produce bioactives that were interacting with the immune system of the host, and some of them actually started to sporulate at the end of their passage through the gastrointestinal tract. So the answer is yes, the microorganism can go, so to speak, through the whole circle and perform well in the host. The first part of the answer to your question. The second part of the answer to your question. The papers started to come, and I cannot say that there were many, but quite a few that caught my attention. And in this case, the investigators were particularly interested in the effect of spores, not the cells. Some investigators were using spores with arrested germination. Some investigators were using spores which were thought to prevent germination, but both groups come to a conclusion that even the spores can benefit the eukaryotic host. And this came to me as a shocking surprise because we know about the variety of signals that are presented on the surface of the vegetative cells. But I was thinking always that, yes, there are some signals on the surface of the spore, but not that many. And yet these are the signals that can contribute beneficially to the eukaryotic host as well. I see one of the questions that there are time problem of biological comparing with chemical waste because biological is growing or dying. Thank you. Yes, of course, biological waste perishability is different. All right. And I think without hesitation, I can say that on average, the biological waste is much more perishable. So the time is really a tremendous issue when we're talking about valorization of biological waste. You're absolutely correct.
Yeah. Thank you so much, Mike.
Thank you for having me. It was a pleasure and honor. Thank you.
Thank you. I'll see you next time.
Thank you.
So we'll go straight ahead to the next talk because it's already 11 a.m. The next talk is going to be by Professor MinTze Liong. MinTze, a next generation agent for healthier gut and brain. She is at the University of Sains Malaysia. MinTze Liong obtained her PhD from Victoria University in Australia at the age of 28. She joined the University of Sains Malaysia in 2006. She has actively published research papers, served as editorial board members of STEAM journals, and delivered keynote and plenary lectures for both national and international conferences. She has also commercialized her probiotic strains and technology to industries in Asia and Europe, in addition to active consultation work for IP, regulatory, and global marketing. For the past 18 years, she has also served as CRO for various human clinical trials in the fields of probiotics, including gut-brain axis, immunity, respiratory health, gut health, children, and infants' health. Professor Liong was named one of the top three young women scientists in Malaysia in 2007 by FWIS L'Oreal UNESCO. She was also awarded the IAP Young Scientist to represent Malaysia at the World Science Forum in Budapest to pitch for changes in science policies in the Hungarian parliament. In 2016, she was named as one of the top research scientists of Malaysia, awarded by the Academy of Sciences of Malaysia. In 2020 and recent, she is listed among the top 2% of global scientists as compiled by Stanford University. So thank you so much, MinTze, but I don't see you there. So is she there? Oh, she's a recorded video. All right. So you can upload the video, please.
Thailand, and Singapore. Hello and thank you everyone for joining my talk in this session today. Before we start, I wish to introduce a little bit of where I am, where I'm from. I'm Leong, I'm from Universiti Sains Malaysia. Malaysia is actually a small country that is sandwiched between Thailand and Singapore. And my university is located in a very small island called Penang in the northern part of Malaysia. So once we cross the bridge from the mainland to the island, that's the campus of our university, Universiti Sains Malaysia, or USM in short. We were established since 1969. Today, my talk will emphasize on three main aspects. The first, we're talking about smaller models. Then we will proceed to human, and we'll look at gut microbiota profiles. So let's look at smaller models. We had two. The first was flies, and the second was rats. We use a very small model of fruit flies called Drosophila melanogaster. It's very small. It is just the size of the tip of a pen. So what happens is that these fruit flies, these Drosophila, are not normal flies. They are actually mutants. They are mutated to represent an Alzheimer's disease model. So Alzheimer's disease is caused by several factors. One of it is the accumulation of amyloid beta peptide in the brain. And because of this, it causes high toxicity, high neurodegeneration, and finally apoptosis to neurons. So we have several parameters that we have adjusted to produce these mutant flies. We use these UAS flies, which already have the Alzheimer's disease gene, but we use a GAL4 promoter to actually exhibit this into the eyes so that we could actually see whether or not these flies have Alzheimer's disease or not. So we have the UAS flies that are mated with the GMR flies to produce these GMR GAL4 line flies. Now this is a very simple microscopic image where we have a positive control, the wild type, with very beautiful eyes, almost perfect in shapes. Whereas the Alzheimer mutant flies, or what we call the UAS GMR mutants, we can see some forms of deformation. Now this is just a very simple microscopy. Let's zoom in to scanning electron microscopy. So for normal flies, the eye structure is rather perfect, where they have a hexagonal ommatidia. Normally we see that as round, but they're not round, they're actually hexagonal. And on alternate angles of these ommatidia, we have bristles. They are like hair-like structures protruding out from each of these ommatidia hexagonal sides. When we look at the Alzheimer mutant flies, this is where we have the GAL4 promoter to exhibit this Alzheimer severity in the eyes. We can actually see that this almost perfect structure is already deformed. Most of the time, we could no longer see clear structures of the ommatidia. Also, some of the bristles are broken, they are malformed, and in certain cases, we can see holes or pores being formed on the eyes. Now, I would like to introduce one probiotic strain. It's called Lactobacillus plantarum DR7, or DR7 in short. So upon administration of this probiotic to these Alzheimer mutant flies, we could see it prevented the malformation of the eyes of these Alzheimer mutant flies. It is not perfect. We could still see some broken bristles. We can still see some hexagonal shapes that are not entirely hexagonal, but it's a lot better enhanced compared to the non-treated Alzheimer mutant flies. So we began to see some positive effects. Because of that, we proceeded next to using a slightly larger animal model, which are rats. For rats, we actually started with one very simple test. It's called the open field test, where we put the rats in boxes, and beyond those boxes are walls. Rats being very explorative and very adventurous animals, they tend to climb on the walls, scratch it, and try to see what's beyond those walls. However, if the rats are stressed or having anxiety or age with cognitive impairment, they tend to be less mobile, tend to stay in the middle, less to the side of the walls. So when we look at our data, this is an aging study. As brain degenerative problems, we have already associated that with aging. We have several groups of rats from our data. So we had young rats, we had aged rats that are equivalent to human of 60 years old. We have aged rats that have been treated with a control drug, which is statin, and aged rats that have been treated with probiotic, Lactobacillus plantarum DR7. As we can see, those rats that have been treated or administered with DR7 showed less number of entries to the outer zone. We also know that as we age, the number of neuron branching reduces. We can see here, comparing between young and aged rats, the number of neurons branching reduces. So we attribute this to neuronal apoptosis, and we also attribute this to a decline in memory and cognitive abilities. Thus, we did another test, which is the Morris water maze. Here, animals are trained to swim, and inside the swimming pool, we will have a submerged platform. Rats were trained to reach that submerged platform. If they remember how to swim there, they would reach the platform faster. So here we have a video that I wish to share with you. So initially we have young rats that managed to find the platform rather fast as compared to old rats, which somehow lost a little bit of their memory, cognitive abilities, they lost their way, and they needed a longer time to reach the platform. Then we also have aged rats that were fed with the control drug statin, which relatively found the platform faster. We also have aged rats that were fed with probiotic DR7, which also found the platform faster, indicating that they have better memory. When we look at the data, indeed, aged rats needed the most higher latency time, that's what we call it, to reach the platform as compared to those aged ones that were fed with statin and aged ones that were fed with DR7. We also had another test called the t-test. So in this t-test, we put food in one of the arms of the T-maze, and rats were trained to remember which arm it was. Was it right or was it left? Then rats were allowed to run freely every time. How many times they actually succeeded in finding the food, which indicate that they remember which arm it was. So when we look at the percentage of correct arm, those rats that were fed with DR7 yielded a higher percentage, statistically significant, in our T-maze test. We also look at the hippocampal properties after sacrificing the rats and dissecting them. So we look at inflammatory factors because neuronal branching apoptosis, even neuronal cells apoptosis, we associate that with inflammation. So we have the interleukin-1 beta, IFN gamma, and TNF alpha, which represented the pro-inflammatory cytokines. And as we can see, in many of these cytokines, rats that were aged but fed with statin, the control drug, or fed with statin and fed with Lactobacillus plantarum DR7, they actually showed a reduction in these pro-inflammatory cytokines. As this is an aging project, we also evaluated on some aging biomarkers such as P53 and P19. The gene expression of P53 was increased in aged rats. However, it was reduced in those aged rats that were fed with probiotic DR7. As we move along, we wish to examine some of the mechanisms, such as which neurotransmitters in the brain that was actually affected by the administration of DR7. I wish to note that in the brain there are 4 distinct neurotransmitters, one being GABA, dopamine, norepinephrine, and serotonin. When we evaluated the gene expression of hippocampus, for all the 3 neurotransmitters of GABA, dopamine, and norepinephrine, we could not see any significant changes due to the administration of probiotic DR7. However, when we look at the serotonin pathway, we saw something. Now, serotonin did not just exist in the brain. Serotonin is formed from the amino acid tryptophan. So tryptophan can be converted into kynurenine or serotonin, depending on which enzyme that's reactive. If the enzyme IDO is reactive, it will convert tryptophan to kynurenine. However, if the enzyme TPH is effective and reactive, it would convert tryptophan to serotonin. And we look at our data of IDO, the administration of DR7 suppressed the gene expression of IDO as compared to all control. But the gene expression of the enzyme TPH, which converts tryptophan to serotonin, was activated or upregulated upon the administration of DR7. Now, it is also important to note that serotonin is the happy neurotransmitter because those patients with a reduced serotonin level in the brain have been reported to have symptoms of mood swings, brain disorders, anxiety, and even depression. We next proceeded to a human clinical study. So for the human clinical study, we published that last year, and we used adults with mild stress, and our finding showed that DR7 could actually alleviate stress and anxiety, but not depression, in this randomized, double-blind, and placebo-controlled study. So the inclusion criteria was that the subjects must be moderately stressed. We used the PSS-10 questionnaire for this evaluation and screening. Upon that, we had successfully recruited 55 placebo and 56 DR7 groups for 12 weeks administration of DR7. Each day, each subject consumed 9 log CFU of DR7. When we look at some of the parameters, obviously from PSS, they were all stressed. That was the inclusion criteria for recruitment. However, throughout 4 weeks, 8 weeks, and 12 weeks, throughout that 3 months of assessment, no changes in total PSS scores. However, when we look at stress scores, we could see that DR7 exerted some effects as soon as 8 weeks in certain groups, especially the younger adults, which were 30 years and below, and overall subjects also 8 weeks. As for anxiety score, this was prevalent in all groups, regardless they are younger adults below 30 years old or older adults above 30 years old, and the effect was seen evident since week 8 or 2 months after the treatment of or administration of DR7. When we look at depression, there was no significant effects. So DR7 did not show any efficacy in alleviation of depression. We postulate that depression is a more severe case as compared to stress and anxiety, and thus DR7 may not be that effective. When we look at total DAS scores, we saw that the younger adults benefited more from the intervention of probiotic DR7 as compared to the older adults, which we did not see any significant. The younger adults, we could see some significance since week 8. Overall, in overall subjects, and since week 8, we could see a total reduction of total DAS scores. We subsequently evaluated some cognitive parameters. We used the Cogsted computerized battery test, where each subject was analyzed using a computer software to look at their memory and cognition abilities. So there are various types of memory and cognitive abilities. One of it will be such as visual learning, working memory, executive functions, and so on. So when we look at all these, we could see marginal effects for the administration of DR7, typically in those adults aged above 30 years old. However, statistical significance was not achieved. Statistical significance was achieved in other parts of cognitive abilities, such as social emotional cognition and also associate learning, where subjects above the age of 30 obviously benefited more from the intervention of probiotics. We also looked at blood parameters. From our animal studies using rats, we could see that DR7 benefited the subjects from hippocampal anti-inflammatory parameters. So for humans, we evaluated on these inflammatory cytokines also in blood. So those subjects aged less than 30 with a more higher stress levels, we could see that the administration of DR7 reduced the concentration of cortisol, IFN gamma in blood, and increased interleukin 10, which is the anti-inflammatory cytokine in blood. Whereas those who are aged 30 with a higher anxiety level, we could see that the administration of DR7 benefited more in terms of pro-inflammatory cytokines such as IFN gamma, TNF alpha, and IL-1 beta. So in terms of all subjects in general, we could see some significant alleviation in blood of these inflammatory cytokines such as IFN gamma and TNF alpha for pro-inflammatory cytokines, and also an enhancement of DR7 against anti-inflammatory cytokines such as IL-10. And in all subjects, cortisol level, which is associated with stress, has been decreased upon the administration of DR7. We also look at blood gene expression of neurotransmitters genes. So from the rat studies, we could see that neurotransmitters mechanism were along serotonin. In terms of human, we evaluated the same thing using blood. So when we look at gene expression of neurotransmitters genes in the blood, this is an inverted data, meaning lower value is higher expression. We could see that for younger adult subjects, older adult subjects, and total overall subjects, we see a rather similar trend, where TPH2, the enzyme that converts tryptophan to serotonin, have been upregulated, whereas the enzymes of IDO and TDO, which converts tryptophan to kynurenine, have been downregulated. So we are looking at the same mechanism of pathway of effects from the administration of DR7 in both rats and also in humans, indicating that serotonin is an important parameter. For older adults and total overall adult, we also saw that the enzyme TH, which was responsible for the conversion along the dopamine pathway, was also down-regulated. So upon stress, dopamine is converted to norepinephrine, and the enhancement or increase of epinephrine in the blood has been associated with increased stress and anxiety in many subjects or patients with brain disorders. Thus, in the human study, in addition to the serotonin pathway, we are also seeing a possibility of administration of DR7 exerting an effect along the dopamine pathway as well. So the conclusion from the human study and animal studies is that Lactobacillus plantarum DR7 probiotic alleviated stress and anxiety along gut-brain axis in both humans and animals via the serotonin and dopamine pathways. And in human, this was very prevalent in both the probiotic treatment group and the placebo group, where we saw not just the neurotransmitters pathways, but also blood cortisol levels, which was reduced by DR7, and also pro-inflammatory cytokines such as IFN gamma and TNF alpha, which was reduced, and an enhancement of anti-inflammatory cytokines in blood such as IL-10 and IL-4, in addition to memory and cognitive functions. We would also like to note that in addition to elevation of stress and anxiety, memory and cognitive parameters was also enhanced. The next aspect that we look at would be gut microbiota, which is an interesting aspect which we evaluated both in flies and also in human. First, let us look at flies. So when we look at the positive and negative control being mutant flies with Alzheimer's disease, we can see a very prevalent abundance of Wolbachia, which was almost zero in the positive control flies. However, those that were fed with DR7 probiotic and also another commercial probiotic that we get in Malaysia, let's label it Y, the abundance of Wolbachia was significantly reduced. And not just that, when we look at PCA plots, we could see that the shift of gut microbiota profiles was actually moving towards the positive control upon the administration of DR7. And this was better than the commercial control that we had in Malaysia. When we look at different abundance of bacterial taxa, we can also see that DR7 resembles more of the positive control than the negative control. And when we look at KGG profiling, we could see that Wolbachia was highly associated with several disorders of the brain, such as Parkinson, Huntington, and Alzheimer's. When we look at human, Lactobacillus DR7 actually modulated gut microbiota, and we managed to correlate that along the dopamine and serotonin pathways in stressed adults. So what we did was that, similarly to the previous study, which had a higher number of subjects, for fecal samples, we only managed to get 99 samples. So out of the 111 that we had, we managed to analyze 99 samples of fecal samples. And what we saw was that alpha diversity, which measures differences within samples, we evaluated using both the CHA1 index and also the Shannon index. So for the CHA1 index, it provides a measure of richness, while equally taking into account of frequent and rare OTUs. The Shannon diversity index, on the other hand, considers OTU's evenness, as it takes into account the frequency of each OTU as well. Both study groups, the placebo and also the DR7 groups, were comparable in terms of both richness and evenness at baseline, and we could see that across different taxonomic classes such as class, order, and genus levels. However, at the end of the intervention period of 12 weeks or 3 months, the placebo group displayed significantly lower richness as compared to DR7 at both class and order levels. So we managed to see some of these as indicated by the green arrows. This shows that the administration of DR7 prevented the reduction of within-group ecological diversity, which was evidently reduced in the placebo group over time. Next, we look at beta diversity, which measures differences between samples. We use the Bray-Curtis index, which considers both the occurrence, co-occurrence, and differential abundance of the OTUs. So compositional differences, again, were not observed at week 0. However, at the end of the intervention, significant differences were consistently observed between DR7 and placebo across different taxonomic levels again, such as class, order, and genus. Now, these indicated that amid stress, within and between samples' microbial richness or ecology was changed or reduced, and the administration of DR7 has aided in the maintenance of such gut microbial ecology to prevent a shift in diversity amid stress. Let us start with phylum. Compared to DR7, subjects administered with placebo had a drop in phylum Bacteroidetes over 12 weeks, accompanied by an increase in abundance of Firmicutes. Now, these changes were also traced to subsequent taxonomic levels. Let us look at the next one, which is class. In the level of class, placebo showed a decreased Bacteroidea and increased Clostridia compared to DR7 after 12 weeks. Further down in the different level of order, we can see that placebo continued to show reduced abundance of Bacteroideals, accompanied by increased Clostridials as compared to DR7 after 12 weeks. A lower count of Bacteroidetes has been observed in patients with altered colonic movements, such as young children hospitalized for infectious diarrhea or patients with functional constipation. Now, this kind of differences was also further trickled down to the level of genus, where Bloschia and Rombosia were increased in the placebo group at the end of the study as compared to DR7. Although Bloschia has been reported as a butyric producer that is beneficial for colonocytes, a high abundance of Bloschia has also been reported in patients with inflammatory pouchitis, non-alcoholic fatty liver disease, systemic lupus, and also breast cancers. Now, there are concerns where limitations have been raised because accuracy and use of higher taxonomic levels are reduced, such as phylum, to predict and correlate with diseases and biological functions. And these are attributed to the vast diversity of human gut microbiota along lower taxonomic levels. Thus, it is strongly noted that in our study, We show that these changes in gut microbiota upon the administration of probiotic DR7 was consistent along different lower taxonomic levels, all the way from phylum to class to order and also to genus. So as DR7 exerted brain health effects along the pathways of neurotransmitters, particularly serotonin and dopamine, thus now we wanted to correlate between these microbiota groups with genes that are involved along serotonin and dopamine pathway. So while changes in gut microbiota upon administration of DR7 was consistent along different taxonomic levels, the correlation of these changes with neurotransmitters genes also shows such a consistency in correlation. Now let us look at one by one. So the phylum Bacteroidetes showed a negative correlation with gene expression of DBH, which was consistent along lower taxonomic levels such as class Bacteroidea and order Bacteroideus. Now DBH catalyzes the conversion of dopamine to norepinephrine. So it's an indication of increased stress as seen in the placebo group with a lower abundance of Bacteroidetes, Bacteroidea, and Bacteroideus. Bacteroidea and Bacteroideus, which were maintained upon the administration of DR7 compared to placebo, also showed positive correlation with TPH2. TPH2 converts tryptophan to serotonin in the brain, where an imbalanced level of serotonin has been reported in patients with psychological disorders, as mentioned earlier, such as mood swings and anxiety. As we move next, we can see a positive correlation was also observed between gene expression of DBH and taxonomic levels along the phylum Firmicutes, class Clostridia, order Clostrideus, and genera Bloschia and Rhodopsia. So Bloschia has also a positive correlation with TDO, which competes with TPH for tryptophan in the brain for the conversion into kynurenine. So reduced level of serotonin and increased level of kynurenine is not actually good and has been shown in patients with anxiety and depressive disorders. So moving down to a different phylum, Delta Protobacteria, we see that its lower taxonomic level of order Desulfovibrilnales and genus of Bilophila, which were both increased in abundance upon administration of DR7, also showed negative correlations with DBH and positive correlation with TPH2. Meanwhile, for Actinobacteria, which showed a lesser increase in abundance upon administration of DR7 as compared to the placebo, also exhibited a negative correlation with TPH2. So all these indicated that the administration of probiotic Lactobacillus plantarum DR7 exerted gut microbiota changes which not only remain in gut but affected and positively or negatively but significantly correlated with neurotransmitters genes along the gut-brain axis. So there are many emerging studies in these years that have reported on the effects of gut microbiota on serotonin and dopamine levels, and also correlate those with psychological effects. However, to our best knowledge, this is the first study on probiotics to correlate between gut microbiota and genes that are related to serotonin and dopamine pathways, which are not only significant but also consistent across multiple taxonomic levels. So this ends my talk, and in summary, Lactobacillus plantarum DR7 showed gut-brain axis benefits in smaller models of flies and rats all the way to human. This strain has been patented in Malaysia, China, Korea, and also PCT. This strain is stored in depository in China and Korea. Whole genome has been sequenced, and human data is available on stress, memory, cognition, upper respiratory tract infection, and also gut health. So if any of you would like to collaborate with me to work further on probiotic strains along gut-brain axis, please visit my website. You can also contact me, and I welcome all levels of collaborations. And this is an aging study. I wish to thank every one of you, your time. The conclusion is I don't mind aging. We all shouldn't mind aging as long as we age healthily. So ladies and gentlemen, thank you very much.
Well, that was great. Since it was a recorded video, I put some information about Dr. Liong on the chat. And if you guys want to contact her, you can contact her there too. and also find her studies. I put this Google Scholar profile to help you find the studies that she presented here, which are quite amazing. Since it's midnight in Malaysia, we don't have Dr. Liong here to answer questions, so that's why I put the contacts. We finish a bit earlier here. We can have a extended lunch break, and we come back at 1 p.m. With the talk from Professor Alexander. I can't pronounce his name. Suvorov. The middle name is just impossible to pronounce for me. Do you have anything to add?
No, I just want to add something. In the moment we are finalizing the memorandum of understanding with University of Malaysia for the exchange of the students between Faculty of Pharmaceutical Sciences and Faculty of Pharmaceutical Sciences there in Penang, where Professor Liong is working. So there will be even more options for the students to interact and be involved in the research projects on the both sides.
Awesome. Great news. All right. See you guys soon at 1 p.m. Brazilian time. Hi, everyone. Good afternoon. Welcome back. We continue our winter school now with a... just a minute. It's all right. Okay. So we're going to have a talk about mucosal vaccines as vectors for mucosal immunology from Professor Alexander Suvorov from the Russian Academy of Science. Professor Alexander is a medical doctor from the Leningrad Medical Institute. He has a master's degree, a PhD, and a postdoc from the Institute of Experimental Medicine at the Department of Molecular Microbiology in St. Petersburg, Russia. Has been a visiting scientist, visiting professor at the University of Leiden in Netherlands, University of Minnesota, US, University of Oklahoma, also in the US. He was the head of the Laboratory of Pathogenic Microorganisms in the Department of Molecular Microbiology at St. Petersburg. And currently, he's the head of the Department of of Molecular Microbiology at this university, as well as the head of the Department of Fundamental Medicine at the State University of St. Petersburg. His research fields are on molecular genetics of virulent streptococci, genetic organization of bacterial genome, genetic transformation of bacteria, vaccine development, among other themes. So, Professor Alexander, thank you very much for your participation, and I give the floor to you.
Okay, if everybody can hear me, I need to tell that I'm extremely happy to be with you today in Brazil, in winter Brazil, being in summer Belarus, as a matter of but I'm trying to speak today about several things which are related with human health and immune system and immunological protection, which is a little bit far from probiotics, which we was hearing a lot, but I think it is still all related. Because now probiotics are becoming a fairly interesting aspect for using for the vaccination. So talking about vaccination and vaccines, not long before, about 80% of all the deaths of the human beings were because of infectious diseases. And one of the most devastating disease was a smallpox, and, but at certain period of the development of science, people realized that if you use material from the pesticides from smallpox, you can get...
Excuse me.
Yes.
The slides are not showing. Could you share them, please?
Oh, I was trying to share them. Boy. Everyone can see and hear, but
not yet.
Not yet. All right, window again. Can you see it now?
Yes, now we can.
Okay.
If you could go back to the first slide, maybe. So just the
first slide was from and can you see the first slide now?
Yes.
Okay, this is the second one. So at certain point of the history, people realized that taking the material from the pustules of the patients with the smallpox, you can significantly decrease the mortality rate. and it was a nice recent discovery from Russian famous museum, the Hermitage, was a set of china obtained British medical doctor Dimsdale, who was violating and protecting from the smallpox the Russian Queen and the Prince Paul I. But still, a lot of people were dying from this kind of procedure and vaccination. So we can rate Edward Jenner as a father of vaccination because he was the first who discovered that if you take the pustules from the cow and the cow's smallpox being injected in the human skin was protecting the humans from the cow disease. And on this picture, you can see that a lot of people didn't accept it at first and they were mocking at Edward Jenner. But finally, this kind of procedure opened the air of immunology and protection, because in reality, any kind of vaccination or any kind of vaccine follows the route of different or any kind of infection agents, because any pathogen presents the antigens from the disease to the helper T cells, and then they can go by two routes, producing antibodies or cytotoxic cells, and put some information about those antigens into the memory cells, which can boost the appearance of the antibodies and cytotoxic T cells after second appearance of the pathogen. So, not surprising, vaccination took place in all of the countries of the world, and you can see that a lot of different procedures were used to make vaccines, including recombinant proteins, mRNA material, DNA material, full pathogen material, and they are. And finally, we can conclude that vaccination as a procedure is adding to the life of the human being about 25 years at the average. And we can see that no matter what vaccine is used, most of the vaccines used for introduction of the antigen to the immune system have been done employing injections. Even most normal mRNA vaccines are supposed to be injected under the skin, which is not very normal route of the infection. But if you look at the whole process of finding the antigen which you want to use for the vaccination, it is not that simple, because there are a lot of antigens in viral or bacterial pathogens, including group A streptococci, which is presented on this very picture. I hope the slides are moving now. But anyway, careful selection of the antigen is very, very important, because those antigens can be quite different. They can be from the polysaccharides, which are not provide the long immune memory, or they can be from the bacteria, which bacterial proteins, which do provide memory, but some of the antigens can be variable in bacteria or in the virus, as you know very well after COVID infection. And this is causing the pharmaceutical companies and researchers to change the amount of the antigens which are introduced in the vaccines all the time. But vaccine are changing, but they are not changing as fast as pathogens are changing. You can remember the Lewis Carroll's story about Red Queen dynamics, which supposed to run in order to get at the same level as the queen. Bacteria or viruses are quite variable, and going in this kind of straightforward logic, when you just try to kill the pathogen without taking care of what is going around, sometimes you are not getting very good results. I can show you the old experiments from my department when we were trying to get and make vaccines against group B streptococci. So if you use just one of each antigens for vaccine protection, you get some decrease of the number of bacteria in different organs of the experimental animal. But if you use all 5 of them, then you get absolutely complete depletion of the pathogen out of the organism of the animal. That is why you get kind of geometric increase of immune protection if you use several antigens altogether. That's why we were able to make this kind of vaccine, which can go and protect newborns from the group B streptococcal infection a lot better than mono vaccine preparations. This teaches us that multiple vaccine variants are a lot better than variants which are containing only one target, because bacteria can change. One of the recent development of our department was vaccine against group A streptococci, which is on the trial now, which has 2 components, one against biofilm variant of streptococci, and another is against planktonic variants of bacteria, which can cause strong invasive infections. Following this strategy, at another part of investigation, we managed to develop the vaccine against Streptococcus pneumonia, which also has 3-component chimeric vaccine, because you can join antigens all together with internal adjuvant. And recently, our collaborators from Argentina showed that this very vaccine is comparable with novelly developed pneumovac 23 vaccine by the Pfizer. So why I'm telling you all these stories about vaccines and approaches which were which were used in my laboratory. I just wanted to show that ideology of vaccination, which started at times of Pasteur and Jenner, in reality didn't change much. But what we can see in reality, we can see that the structure of pathogens do change. We have new viruses in the world, like SARS-CoV-2 epidemics which happened recently. We have new pathogens which presently are in many clinics, like escape pathogens, which previously haven't been considered serious threat for the human beings. So we do have significant changes on the scene. And what is another thing which I want to mention that medical attention was only addressed to the elimination of the pathogen which was causing the problem, without mentioning that introducing the vaccine can significantly change the microenvironment and microbiota. And at the same time, as I said, most of the vaccines on the market are injectable vaccines. However, pathogens introduce our body through the natural openings of our organisms. So the first barrier for the pathogen is our own mucosa, and mucous surfaces are covering our cavity in the mouth, our nose, or our intestinal system. That is why most recently people are thinking about designing antigens against or again the pathogen, employing mucosal vaccines, which give the rise of the very specific antibodies and antibodies of class A just on the mucosa. And the most organ which get an access of the antigen is our gastrointestinal tract. If you remember the physiology, you remember the tremendous number of Pierce patches, lymphoid follicles, which are filled with so-called M cells, which process and take the antigen and present the antigen to the immune system. So about 70% of all the antigens which our immune system accepts go through the intestinal barrier. So they go through the mucosa, they're accepted by the M cells and dendritic cells, and then the organism reacts with immune globulins of class A and class G, which are protecting our body. So if you look at the gastrointestinal tract, it is inhabited, of course, you know it very well, and it has natural inhabitants which live there. And if you look at the bacterial content, many of those bacteria which naturally inhabit our intestinal tracts now belong to probiotics. We can remember our great Russian microbiologist Ilya Mechnikov, who first introduced the idea of probiotics using cultured lactobacilli. But most of probiotics on the market originally came either from cattle or from the human beings, and they come from the intestinal system. And one of the most common inhabitants of our or animals or chicken intestinal system are enterococci. So we decided to look closer at enterococci as possible vaccine delivery systems. Who are these bacteria? They are milk fermenting bacteria, which are normally inhabit the gut and mammals of the birds, and they're involved in making of the foods all over the world and produce a lot of different antibacterial agents. So the original idea of mucosal enterococcal vaccines was to use enterococci instead of the other antigens in the same scheme which I showed you at the third slide, and put the antigen on the surface of the bacteria in order to give rise to both adaptive and innate immune system. To be true, we are not the only group which is working on probiotic vaccines. Now there are several recent studies using different bacteria as probiotic vectors for vaccine antigens like bifidobacteria or Escherichia coli or lactobacillus. Several strains of lactobacillus also can be genetically manipulated and present the antigens to the immune system. This is a very general way of making probiotic vaccines. So what you do, you take the vector which can propagate in the probiotic strain. You can use the vector in the plasmid form, put it inside the bacterial cell, harvest this bacterial cell, and then introduce it into the organisms through the tablets or capsules in order to get robust immune response, help to protect against the infection. Such infection like SARS-CoV-2 and pretty much the same what we do employing our enterococcal vaccine. We, as a matter of fact, we used a very well-studied enterococcal probiotic strain L3, which is completely genetically evaluated and has a lot of interesting features which allow us to do genetic manipulations. But returning to SARS-CoV-2, two major parts of the virus are the target for making vaccine. It is so-called S or S1 or S2 proteins, which are just on the surface, and N antigen as well. And these two antigens are most variable parts of the virus, which is important for developing of vaccines. So what we do, for example, regarding the S protein, we will take the gene encoding for part of the S protein. Basically, it is a receptor binding domain, and then genetically introduce it in the gene responsible for fimbria assembly. And if you make it inside the gene for fimbria, like basic gene for fimbria, you can eventually make bacteria which is having fimbrias with the antigen of your choice on the surface. So on the left part of this slide, you can see fimbria of Enterococcus faecium with a lot of dots obtained after immune gold labeling is against S protein. And the control on the right shows that the bacteria originally didn't have this kind of antigen. So we made a couple of constructs which cover most of the present variants of SARS-CoV-2 mutants, and started doing some experiments regarding immunology and protective efficiency of the vaccine. And you can see that it provides general immunoglobulin G, and what is most important, immunoglobulin A response in experimental animals. and at the same time it provides pretty strong interferon gamma response, which tells you that the innate immune system is also completely involved in protective studies. And in the animal models on the lungs of the Syrian hamster, you can see that if you look, for example, at the control animals in the lung, you can see a lot of blue dots representing lymphocytes in the lung tissue. But if you look at the lungs of the animals vaccinated by one of the products, you can see that it is completely free from these activated lymphocytes, and the animal is completely free from the virus by the day 6. So the advantage of such SARS-CoV-2 vaccine showed us that this kind of approach, being simple and quite effective, can use just general milk product with any kind of antigen or antigen of your choice in order to get protection against viral infection. But we can remember that all the viral infection are followed by pathogenic bacteria, so we can do vice versa. We can take influenza virus used for vaccination and genetically modify the viral DNA as it is, substituting the part of the virus gene with the genes from bacteria, and get nice protection against both virus or bacteria employing this kind of strategy. So presently we are making vaccines with probiotic and like enterococci probiotic, which can provide protection against both viral infection or bacterial infection. For example, this is one of our recent study of the joint combinatory vaccine against strep pneumonia together with influenza virus. And we can get very good results protecting mice against both influenza and even different kinds of influenza. So this kind of vaccine made by bacteria can provide you general protection against different influenza viruses, which are coming independently on the virus. All at the same time refers to bacteria, because if you look at the bacteria against strep pneumonia, it is protecting against different capsular serotypes of strep pneumonia, because it is used very conserved surface expressed antigens in chimeric construction, which are expressed on the surface. So generally speaking, using this kind of technology just can change the bullets in your vaccination platform, and you can make platforms on this very platform, make vaccines against group B streptococci, group A streptococci, meningococci, retrovirus, and so on and so forth. And about 8 different vaccine candidates are made in our lab so far. So this very study give rise to certain thinking regarding the present vaccination and the place of the probiotic in the way of fighting the infections. Because if you make a novel vaccine, and presently there are appearing vaccines against staph and we are full of staphylococci. Some of them are quite important for us. We don't want to eliminate all staphylococci of our body, or enterococci, and we don't want to eliminate all enterococci from our body. So elimination of microbiota must rely not just on pathogenic group of bacteria belonging to one species, but it should be targeted to pathogenic representative of the species, not just against the species as it is, but just against the bad guys in this very species. And there is another thing which is important, that before the vaccination, you need to monitor the condition of adaptive and innate immune system, and only then immunize, because we can see a lot of side effects of immunization. And employing probiotic vaccine technology, you can nicely avoid side effects of injectable vaccination, because in our hands, oral vaccination have a lot of advantages regarding safety and productivity, because we never get very high immune response regarding antibodies, but we have very good protection effect regarding real fight against the infection. And what is another thing which we need to memorize, that using vaccines with multiple epitopes is quite efficient in order to avoid the red queen phenomena and immune evasion. So, but not least, is what we can add to the ideology and strategy of making new vaccines, that we can make both viral and vaccines against bacteria altogether, in order to avoid bacterial complication after the virus infections. So basically, that is what I want to tell you, and sorry for poor presentation because of some kind of technical problems. I hope you saw the slides, and I will be open for the questions at least. Thank you.
Well, thank you very much, Professor Suvorov. The floor is open for questions, if we have questions here. Professor Slav has a question.
Can you hear me there?
Yes.
Well, thank you very much first for the presentation. And by the way, I try to teach the Brazilians with the Slavic names, but still I have a problem. They learn very slowly to pronounce our names. Now my question, it's I already am quite familiar with this project that you have, the develop of the vaccine and using the fermented milk products as a delivery vehicle. Now my question is, we know that the COVID virus changed very quickly. And now if we move to another variant of the COVID, the developed vaccine that you already have will be active against new variant, or you need to develop the new variation of the these modified strains in order to be effective against the new variants?
Thank you for the question. It is Red Queen dynamics at full scale, what we see with COVID infection. Presently, we have fairly good variant against novel novel variants of Omicron, so they're quite protective. But we were running behind the virus, just making new and new variants against COVID. You are correct that basically this strategy is not 100% productive, but maybe I was a little bit nervous because of the poor presentation, but I didn't show that we were using conserved variants against N protein, which is quite conserved, and against variant of on the S protein, which is also not mutated as much as RBD domain. So in our hands, N protein and this kind of conserved variant worked very well in our models on mice and in hamster. So I still believe that the vaccines we have can be quite useful for the people because they have Omicron variants as well.
And I'm actually very in the favor of what actually you're doing there, because this is a way of much more the protection, prevention, because this fermented drink products, actually it's something popular drinks. And if we can deliver the protective vaccine strains by these popular drinks, it's a perfect way to protect the population. So rather look for the prevention than when we have the problem to look to how to solve the problem. So it's a very, very good approach.
I can tell you one thing which we didn't think of before starting those experiments. We used the original strain L3 as a control in all our studies because it was used for genetic manipulations. But the problem which we were running into was related to the fact that probiotic itself tend to work against COVID very, very nicely. So we were really trying hard to find the difference. We did see the difference in immunoglobulin response and immune memory, but in real experiments, our control probiotic strain also was very good against COVID. So even just probiotic can help you to diminish the severity of the disease. That's what we saw for 100%.
Well, maybe even some proteinase inhibitors produced by some of these bacteria could be involved in the entire process, but this is a completely different story and different page for research and evaluation.
Yes, yes.
Do we have more questions from the audience?
Hello, Professor. Why did you... Can you hear me?
Yes, yes, I can hear you.
Why they use for Enterococcus faecal rather than other species? Why this specific
Actually,
this kind of organization?
The reason was simple. By the accident, we have done a lot of study on this very strain as probiotics, like previous speaker, who was working on lactobacillus E7 a lot. But in reality, we were quite happy that we have chosen this very strain because it is very robust and you can do genetic manipulations, and it has very good and clear genetic construction of the genes involved in fimbria development. So you can manipulate genetically with this fimbria. I couldn't show you all the kind of molecular genetic tricks we used, but basically now you just can use specifically introduced restriction enzymes to cut it out of the chromosome and do PCR and introduce the gene of your choice. So I believe that you can do somewhat similar on lactobacillus model, and I'm willing to try it, but you need to have the basic methods behind your back before you just jump on another bacteria, another subject.
There's more questions? Actually, I can add something, because one of your papers, you are defending very strongly enterococci. There's a paper published in the Journal of Probiotics Antimicrobial Proteins on the enterococci that you was having a very nice overview on the importance on the enterococci and the fact they are not such a bad guys. Actually, they're quite good, and we can do a lot of work with them. And I know why this student was asking questions about the enterococcus, because he worked with enterococci. I want to be sure that his strains could be considered as a good. So I don't think we have more questions. So thank you very much for your participation today. It was a pleasure to see you with us. I hope to see you next year in March here in Sao Paulo on the Yakult conference that is planned to have you here. Maybe see you in October in St. Petersburg. And really, thank you very much again for your participation.
Thank you. And I hope that you will come in October to St. Petersburg. It will be nice, very good conference, I'm sure.
I know I was already participating online in a couple of editions, and always amazed how you can combine the presenters from all around the world. And the more important, it's for free. You don't charge the students to attend the conference.
No, it is completely for free. It is completely for free. Thank you.
Okay, thank you very much, and see you soon.
Goodbye. Thank you.
Now we have a break until 2 o'clock, where we start again. Hi there. Can you hear me? Hello?
Sorry, I have some issues. Give me 1 second.
All
I
right.
cannot hear you. Give me 1 second.
Maybe he's having trouble with the audio.
Ya está la cámara. Ya está la cámara. Hello, can you hear me now?
We can hear you.
Perfect.
Hi.
Yeah.
Well, welcome. Good afternoon. I don't know if it's afternoon already there.
Good morning. Thank you.
All right. So we're going to continue now with a talk from Professor Jorge Henrique Vázquez Bukele from Universidad Nacional Autónoma de Chiapas, Mexico. He's going to be talking about fish flow, a novel methodological framework for assessing antibiotic resistance and virulence factors. Professor Jorge has a PhD from Hangdong Global University on biomolecular approaches in evaluation of microbial communities. His supervisors were Huzapfel and Professor Todorov. He also has a master's degree from Universidad Nacional Autónoma de México in Ciências de la Salud, and he has experience on molecular biology. So Jorge, thank you very much for joining us, and I hope you can start now. Let's see if your presentation loads.
Okay, give me a second. I will upload it. Give me a second, please. I'm very sorry, but I am working on a Mac and I don't know how to. I am asking for help.
Okay.
No. It's it's presenting.
If it is a new Mac, that's problematic because it asks
Yeah,
a
it's
lot
really
for
difficult.
allowing you to share.
Can you see it now? Can you see?
I can see.
Okay, thank you very much. Okay, sorry for the issues.
We still can see the presentation.
Can I start now?
Not yet. Lara, is the presentation on? No?
Yes, I'm sharing right now.
Yet?
Not yet?
Not for us.
Not for us. Okay, give me just a second. Yes, I'm trying to share the screen, but maybe all the screen.
Yes, best if it's in the whole screen. I think it's easier.
Yes. Okay.
Okay.
I think
yeah. Now
yes.
it's perfect. Now we can see it.
Okay, perfect. Well, sorry for all the issues. Thank you very much.
No worries.
Good afternoon, everyone. My name is Jorge Enrique Vázquez Bukele, and it's a great honor to be here today. I would like to extend my gratitude to the University of Sao Paulo for this invitation. And today I will be discussing a novel methodological framework known as fish flow. This innovative approach is designed to study bacterial communities and assess antibiotic resistance in various factors. That these are two critical aspects in the field of microbiology and infectious disease control. And that's why understand and address these factors is imperative for improving animal health and ensuring sustainable livestock production. So, in today's presentation, I will explain through several sections that will help us to understand the fish flow framework in depth. We will start with an introduction for the importance of the microbiota and antibiotic resistance in the current methods used to study it. Following this, I will talk about methodology of fish flow, explaining the technical details and how this integrate both fish and flow cytometry. Next, we will conduct a comparative analysis, highlighting the advantage and limitation of fish flow compared to other existing methods. And then I will present various application results, showcasing the case studies, interpreting data, and finally, we will go to future direction, research, and improvements in this field. Finally, we will go to the conclusions. Let me start talking about a bit of the intestinal microbiota that is really important for us. It comprises around 38 million trillion of bacteria. And to put this into perspective, this number is equivalent to or even surpass the number of cells to the human body. This immense bacterial population highlights the crucial role of gastrointestinal system as one of the primary interfaces between host and environment. These bacteria not only aid in digestion, but also play vital roles in immune function and overall health. Understanding this is essential for advancing our knowledge in antibiotic resistance and pathogenic pathogen factors. So, when we examine the human microbiota across different systems, it becomes evident that the gut tract is a predominant site. It harbors a staggering number of bacteria ranging from 10 to 13 to 10 to 14, and this means that the gastrointestinal tract can represent more than 99% of the total bacteria in human body. Of course, depending on the context and the specific conditions, but this underscores the critical role of gastrointestinal microbiota in maintaining overall health and interacting with environmental factors. So other areas are really important in our body, like the skin, genital tract, respiratory system, and have important functions, but are far fewer in comparison with the gut microbiota. This microbiota performs several vital functions in the host. It will contribute to overall health and well-being. One of these primary roles is the extraction from energy from the food, aiding the digestion and absorption of nutrients. Additionally, microbiota is involved in the production of essential vitamins that we cannot have it normally in diet. Also, maintains the integrity of the mucosal barrier, protect against pathogens, and prevents inflammations. The gut microbiota also regulates appetite and plays a crucial role in controlling pathogenic bacteria and is indispensable for us in the immune system development, training the immune system to detect harmful and harmless entities. So that's why it's really important for us in our body. And that's why the phrase that says that we are what we eat holds profound truth when it comes to our gut microbiota. Our diet plays a significant role in shaping the composition and functionality of our microbiome. Probiotics found in whole grains, fruit, and vegetable consist of indigestible fibers that will nourish beneficial gut bacteria that will get us a healthy microbiome. On the other side, we have probiotics that present fermented food like yogurt or kimchi, and that will introduce leaf bacteria and will enhance our diversity. On the other side, we have processed foods that we know that is already very high in sugar, fats, salts, that will cause dysbiosis in our body. And finally, we have also in the diet the plant-based proteins that will promote a diverse and healthy gut microbiota, providing essential amino acids and fibers that will together compose all our microbiota. Sorry. The composition of and function of our gut microbiota are influenced by various factors, including age, gender, emotional state, and lifestyle. As we age, our diet evolves, starting from breast milk when we are babies, and this will promote the development of different bacteria, like bifidobacteria, that are really important bacteria to us, that we are losing it as we are aging. Also, there are gender difference because of the hormones, lifestyle. Furthermore, if we have a different diet, exercise, sleep, or even medication, it will impact in our gut microbiota, and we can have homeostasis and dysbiosis that we get disorder or disease in these cases. So that's why it's very important these communities in our body because they will help us in defending against pathogens through several mechanisms. First, there is competition for resources. The beneficial microbes occupy niches that would otherwise be available to pathogenic organisms. Thereby, it will limit the growth of them. Second, many gut bacteria produce antimicrobial substances that, like bacteriogens. This will directly inhibit or kill the pathogens. Then also the microbiota strengthens the gut barrier, maintaining the integrity of the mucosal lining to prevent the pathogen invasions. And another key that I didn't tell you before is that also they contribute to maintain an anaerobic environment. With this, many pathogenic bacteria won't be able to grow, and all these mechanisms together will help us to maintain healthy organisms. Then, building on the critical role that the gut microbiota plays in pathogen control, it is important to address the impact of antibiotic in this delicate system. The indiscriminate use of antibiotics over the years has led to emergence various superbacteria. We call it also antibiotic-resistant strains. These resistant bacteria are not always pathogens. There could be also probiotics or commensal bacteria that we found commonly in the foods. And this is why it's very important for us to keep a control. If we have a very good quality control in the food process, we can ensure that our gut microbiota will keep in healthy, and also that we don't make any transfer of these resistant genes to pathogen bacteria. Antimicrobial resistance is a growing global crisis. Just in 2019, over 1 million deaths were directly attributed to antibiotic-resistant bacterial infections. This is a really alarming statistic, and that's why we need to take an urgent action on it. The widespread nature of this affects individuals across all ages and regions and make a really global threat. Comprehending this problem is a fact that the problem is that we don't have any antibiotic discovery in the recent years. So it's very important to use the new alternatives like bacteriogens in order to control this, and also control the food process to don't get any resistance on it. Let's put an example. In vancomycin-resistant Enterococcus, there is a rising threat on the antimicrobial resistance. Although the detailed information for more recent years is really limited, the existing data already paints that it's really concerning. This resistance has increased over the years and has high morbidity and mortality. Just in Germany, in a lifespan of 10 years, it has increased around 54% and is really dramatic. So that's why we need to increase it in order to take action on it. That takes us to the question, how do antibiotic-resistant bacteria spread? This is a crucial question that we must address. There are several mechanisms, but today I will focus on two key forms: selective pressure and horizontal gene transfer. Starting with selective pressure, when antibiotics are used, they create an environment where only the strongest, more resistant bacteria survive. This is particularly problematic when antibiotics are not taken at the correct doses or if treatment is stopped prematurely. The surviving resistant bacteria then replicate, leading to a population that is increasingly resistant. Over time, this selective pressure ensures that the entire bacterial populations become resistant, making infection harder and harder to treat and control. In addition to selective pressure, we have the antibiotic-resistant bacteria that can spread the resistant genes through both methods, vertical and horizontal gene transfer. Vertical, we already know that is when the replication occurs, the cell division will pass the resistant genes from parent bacteria to offspring. Then, this will ensure that successive generations inherit this resistance. But we have one that is really dangerous for us, that is the horizontal gene transfer. It involves the transfer of genes between bacteria, even of different species. It could be from probiotics to pathogens and from pathogens to probiotics. This involves transformation that uptake the free DNA fragments from environment and bacterial cells, transduction that bacteriophage infect bacteria and can transfer this genetic material among them, and conjugation that involves direct cell-to-cell contact, typically through a pilus, and then transfer the plasmids containing resistant genes. We will see this further in this presentation. Returning to the example of vancomycin resistance, there are 8 different genes responsible for resistance to this antibiotic. The most frequently encountered is in hospitals is BAN-A and BAN-B. These genes can be transmitted through plasmids, facilitating the horizontal gene transfer among bacteria. But how this resistance works? Well, it involves the alteration in the bacterial cell wall precursors. Normally, vancomycin binds to the D-alanine-alanine terminus of the peptidoglycan precursors, and this will inhibit the cell wall synthesis. However, in resistant bacteria, the BAN-A encodes an enzyme, and this enzyme will change the D-alanine-alanine terminus to alanine lactate. This modification will reduce the vancomycin binding affinity and will allow the bacteria to survive in the presence of antibiotic. That's why it's really important for us to make a prompt diagnosis, because if we make a fast diagnosis on it, we will quickly take actions and we will apply the efficient strategies for it. But how does the food production contribute to antibiotic resistance? Well, it's really easy. On one hand, we have that the antibiotics are administered to livestock. And historically, they were often used to improve production parameters, even if it was not medically necessary. However, this has been diminished nowadays. But this practice led to the development of resistant bacteria, and this resistant bacteria was excreted in animal feces, and also these feces were used as fertilizer to food crops, and also went to water in some cases. Then, when we sacrifice the animals or we take the fruit of the crops, it will go part as the human food chain. We will eat it, the resistant bacteria, and we will transmit these resistant genes. On the other way, we have the spread of resistance among humans. We will take antibiotics, and if we have not completing the prescribed course or using antibiotics with the proper medical guidance, it will promote the development of resistant bacteria, and this we will transmit it with interaction with other persons, and also when we go to hospitals, we will develop this resistance. And as I told you before, The livestock farming is one of the major contributors to the transmission of this antibiotic-resistant bacteria. This study made by Line, spanning several years, demonstrates how all livestock species harbor resistant bacteria and show the resistant rates have been increasing over the time. The data reveals a significant rise in the number of resistant cases from 2000 to 2018, with pathogens like E. coli, Salmonella, Campylobacter, Staphylococcus being prominent in the most common species that we use as food. Also, food can affect our health in various ways. It's crucial to understand these pathways. First, foodborne pathogens can cause a range of illness from mild food poisoning to severe infections. Contaminated food is a significant source of these pathogens. Second, food allergies and intolerances can trigger allergic reaction in susceptible individuals. Also, third, dietary imbalance, such as consuming excessive amounts of processed foods, sugar, fats, can lead to chronic problems. But for this study, we will focus specifically on how pathogenic bacteria will contribute to this health risk. Understanding how these bacteria spread and cause disease is critical for developing effective prevention and control strategies. That brings us to the critical importance of diagnostic methods in the food industry. These methods play a crucial role in ensuring safety, quality, and integrity of our food supply. By providing tools for understanding and controlling food production process, diagnostic methods will help us in detecting and manage foodborne pathogens in an effective way. Rapid and accurate detection of pathogen is essential for preventing foodborne illness, protecting consumers, and implementing these diagnostic protocols will allow the food industry to maintain the high standards and protect us. There are many factors that will contribute to select the microbiological method. I here listed the ones that I consider the most important. However, as I told you before, there is a lot more. All of them, each of them has different strengths and limitations. So it's critical for us to consider what is the most appropriate for our investigation. For example, some techniques or some methods consider specific bacteria are more specific or sensitive for certain kinds of bacteria, or cannot detect the resistant genes. Also, the food matrix, the different foods have different compositions, and this will affect the diagnostic method. Also, some foods have different inhibitors that will interfere with the detection techniques. Then we have the time. Sometimes in the time consumption, some methods will require more time than others. I will turn further this, but this is essential. Let's say that we have a breakout of some disease. It's really important that we have a method that we can have results in 2-3 hours. That will be awesome. And also the one that for me is the more important is the cost. The budget constraints often apply a significant role to determine which diagnostic method we will use on it. So I have designed a comparative chart outlining the advantage and limitation of each method of all of these methods. For example, culturing is relatively inexpensive, but can take up to 72 hours to yield results, which can be a significant limitation in hospitals, where septicemic infections require rapid diagnosis. On the other way, we have molecular methods that are highly accurate, but the problem is that they require certain quantity of DNA to have reliable results. Normally, if we transfer this amount of DNA to number of cells, we require about 10 to 1 million of bacteria in order to get a reliable amount. Other method that is frequently used is microscopy, but it's very useful for visual confirmation, but it's not easy to have any comprehensive results about resistant genes. That's why we have to adapt it about the objective of our research. So there are different methods that utilize the DNA amplification, such as next generation sequencing, that are considered gold standards in microbiota analysis. These are PCR-based methods that has revolutionized our ability to identify and study large number of bacteria taxonomy in a population. We can study the microbial populations and even bacteria that cannot yet be cultured in a laboratory setting. We will be able to know that they exist. So that's why it's very important, but they have several limitations. And I'm not saying that these techniques are useless. They are very important for us, but I'm saying that we can use another alternatives for different research. Which are the limitations? Well, first, sequence divergence in priming sites can lead to amplification errors. And this will magnify exponentially the mistakes and will skew the results. Finally, this can result in an inaccurate representation of microbial population. Second, PCR trends to preferentially amplify short sequences potentially overlook longer, more complex genomic regions. Additionally, copy number variation of the target genomes can introduce large bias on it. And the sheer amount of data generated by complete genome sequences is huge. We need really high and costly computers to get all the data and analyze it. Also, if the quantity of DNA is too small, it may fail to detect the resistant population, even if it's present on it. That's why we propose fish flow as an alternative tool for studying bacterial communities. Fluorescent in situ hybridization, also called FISH, combined with flow cytometry, offers distinctive advantage that can be highly attractive to researchers. Unlike PCR, it doesn't require the amplification of the nucleic acid. It uses specific probes that will hybridize with the DNA of the bacteria. FISH is capable to identify individual microbial cells in various media, and this will label the cells that will quantify and differentiate by flow cytometry. This technique allows the analysis from it can detect only 1,000 bacteria. It's really a few amount of bacteria, and also can give us the taxonomy and detect the presence of resistant genes. That's why we can make a multiplex on it. If there are some researchers that already are detecting with fish flow around 30 characteristics in just one assay. We can say that bacteria is a salmonella, identify the taxonomy, and that salmonella is resistant to vancomycin or to erythromycin. It's really interesting. But let's dive into the detailed functioning of fish flow. The process begins with the selecting and designing of the specific probes that will target ribosomal RNA within bacterial cells. These probes are fluorescent labeled to enable detection. Then, the chosen samples are fixed to preserve the cellular structures and then permeabilized to allow the probes to enter the cells. Then, once the fluorescence probes are binded to the target sequences, we will make wash and they will pass through flow cytometer that it will give a signal in order to detect it. So I have updated this chart with fish flow, and as you can see, it's a rapid method, providing result only in 2 hours, and although the equipment and the probes could be expensive, they are highly durable and offer high precision. We can say that the cost around, with fish flow, costs around $10 or $20, depending on the sample. And this will make fish flow a valuable tool for researchers who need a quick and accurate microbiological analysis. The fish flow method offers several significant benefits. I said it before, but let's see a resume. This technique will allow the detection of low level of target bacteria from 1,000 bacteria. Also, compared to traditional methods, provide much faster results. And then it doesn't require pre-enrichment or culture in order to do it. And it can work with different kinds of samples. Also have a variety of practical application in food safety. This technique allows for the swift identification of foodborne pathogens in food samples. It can detect harmful bacteria such as Salmonella. Moreover, it can identify specific genes of interest like antibiotic resistance or virulence genes. And by regularly assessing these microbial populations, it helps in maintain a clean and safe processing environment. And in this way, we will keep the high standards for food safety. The number of publications related to fish flow has shown a steady increase over the past decade, indicating the growing recognition and adoption of this method in scientific community. This trend highlights the value and effectiveness of fish flow in various research applications. As you can see, this literature demonstrates how researchers are leveraging the benefits of fish flow to achieve rapid, accurate, and detailed microbial analysis. I will emphasize the successful application of fish flow techniques in various research areas. Each of these examples show the versatility of fish flow in analyze the to characterize bacterial communities. They have different applications, they have different objectives, all of them, but they have something in common. They want to study the bacterial communities, and they made it successfully. With this, in this chart that we can see here, it was performed with fish flow, and it's very similar with these ones that we can get with sequencing, and it's much cheaper than metagenomic analysis. So, I will introduce to two specific studies that we conducted before using fish flow method. First is the characterization of gut communities to analyze the composition and diversity of gut microbiota in fecal samples, and the other one is the detection of antibiotic-resistant genes to detect these genes in bacterial populations. I want to mention that we use peptide nucleic acids in our analysis. These PNA probes offer several significant advantages when used in fish techniques. First, they have higher affinity and greater specificity compared to DNA or RNA probes. This is because PNAs lacks the negative charge of the phosphate backbone found in DNA, and this will allow them to bind more tightly to their complementary sequences. Additionally, PNA probes are more stable than DNA or RNA probes, and they require more lower concentration for hybridization. So we began by dividing the mice in 4 different groups, 1 control and 3 groups of stressed mice by different methods. And from each group, we collected the fecal samples. Then we suspended the samples and dilute up to 0.5 optic density. Then we fixated the cells with paraformaldehyde and ethanol. And finally, we performed the hybridization. Finally, to read it in the flow cytometer. Before that, we tried to make the specific probes as much as accurate possible, following the guidelines. For a good probe, we need to use the PNA bio2, and the ideal probe have to be between 50 and 80 degrees for a multiplex assay, base count of 12, purines left at 50%, a low amount of GCs. Also, give free energy between -20 and -12. These parameters will ensure that the probes have the necessary stability and specificity to hybridize with the target bacteria. And then, using the RDP database and SILVA database, we compare these sequences with target bacteria and non-target. That we will focus on only the phylum because they are the most important. These phylums are the ones that most change when the mice are stressed. Is Bacteroidetes, Firmicutes, Proteobacteria, and Ectobacteria. We only designed 3 of them, compared to another non-target bacteria, and it was successful. They have high specificity and high sensitivity in the analysis in silico. So we started with the optimization of the hybridization temperature as we show here, and they have highly specific to their targets. We can see that at first at 66, at the temperature of 66, we have a high hybridization, a high detection of all the bacteria that are representing each phylum. However, as we increase the temperatures, the detection of these cells is decreasing. When we try it in different bacteria like Actinobacteria, Bacteroidetes, Firmicutes, and Proteobacteria, you can see that there's hybridization only for the specific bacteria for this phylum. And from other bacteria, if it's not the correct hybridization temperature, we will have on a specific hybridization. But when we reach the specific hybridization, this hybridization will, on a specific target, will get decreased. Then, when we optimize the temperature, we got to the single cultures. We make, for any bacteria that is representing each phylum, get the detection on it. Then, we perform hybridization, and we look for the universal bacteria that we got detections from more than 90%. We can look it here in the results of the flow cytometry. When there is hybridization, the cells will give a signal to the equipment and will increase the signal, so we consider it here as positive. And if there is no signal like this control, it will perform here as negative. So when we get to Bacteroidetes and Firmicutes in the single cultures, we get that Bacteroidetes got a good detection, but the other phylum didn't. Firmicutes got a really good detection compared to the other phylums. Proteobacteria the same, we get really detection of 84%. However, Actinobacteria wasn't that good, because even we have a good detection for the bacteria, a specific bacteria, we have on a specific detection, hybridization for them, so it's not really got this proof. Then we work with the mixed cultures. We make a mix of different bacteria representing each phylum in equal proportions, around 25% each bacteria, and mix it. Then for the bacteria, we have 25% of Bacteroidetes Omicron, and we have a very nice detection of 29%. Is really nice result. Also for Firmicutes, that is Lactobacillus plantarum, is around 31%. For Proteobacteria, also we got a good result. For E. coli, it's 21%. But Actinobacteria, we have on a specific detection, and we have a really high result of 39% of the total population. Then we wanted to use it here in our fecal samples, and we discovered, according to literature, that fish was, according what we say, in stressed mice. For example, literature says that in the present mice, the Bacteroidetes population will increase, and we have an increase on it, on this population, compared to the control. Also, we have that Firmicutes will get a decrease, and we only found it in combs, and the other is not significant, but still we see it in one of the groups. On Proteobacteria, it says that will increase, but we didn't have any particular detection on it, significant detection. And for Actinobacteria, we didn't detect any difference on it. So then we wanted to compare the results with qPCR to see if they are comparable. And we found that the results are very similar, and also the tendency of the bacteria is with qPCR and flow cytometry are very similar. We have more Firmicutes than Bacteroidetes in both. And finally, when we made a comparison with metagenomic sequencing, we found very similar result. There wasn't any significant difference between these two methods, but we have a very interesting results. The methods that were made with sequencing have a greater variation than the methods that were made with fish flow. You can look at here. It was really low, the variation with fish flow, and very high with metagenomic sequencing. Then, now we tried to make it with BRE, detection of vancomycin-resistant genes. So we selected 12 different isolations from hospitals and performed the detection of the genes. We tried with the 6 different genes, and as I told you before, the most important genes that are in hospitals are BAN-A and BAN-B. And we have the presence of these genes here and here, BAN-A and BAN-B. So now that we know that they are resistant, we made the fingerprint and detecting that there are 6 different strains. And finally, we make the, again, the detection of resistance versus vancomycin. Finally, we made the fish flow assay, but we detect that it was almost all negative. We have results of 2 or 5% with the probes, and that was really interesting for us. So we decided to repeat the assay, but now in a different way. We make a culture with a plate without antibiotic and now with antibiotic of 100 different CFUs from the same strain. And then we observed that all the CFUs grow in the plate without antibiotic, but only a few grow in the plate with antibiotic. That means that if the bacteria doesn't require to defend against this antibiotic, it will lose the plasmid on the way. And that's why we have very loose detection of the bacteria, but still we have it. So when we make the detection of the bacteria to the susceptible, the ones that grow in the antibiotic, we notice that we only have a growth of bacteria of the resistant genes only about 3% of the populations. But what happened when we selected these bacteria in the vancomycin resistant plates? We have a really different results. We have detection of the gene around 51%. It was really good result. So, in this way, we confirmed that we can detect resistant genes with the flow genes, and we can also detect the bacteria that doesn't have the genes. Then, with these fish flow methods, we can rapidly detect pathogens and their specific gene of interest. At the same time, if we make a multiplex assay, we can detect it very quickly and a lot of characteristics at the same time. It's very accurate and it's very fast to do it, and it will enable scientists and healthcare providers to respond swiftly to potential health threats. So, in conclusion, our findings demonstrate that the effectiveness and reliability of fish flow method is very good. This method offers distinct advantage over traditional techniques. It's faster and it has high specificity. And the impact of fish flow extends beyond the mere identification. It has a significant role in microbiota research, particularly in areas such as gut health, food safety, pathogen monitoring. Additionally, it plays a crucial role in understanding antibiotic resistance. And from a practical standpoint, it has a diverse applications like clinical diagnostics, environment monitor. So there is I encourage for further research and development in fish flow in order to advance in diagnostic methods and improve the public health outcomes and address the growing challenge of antibiotic resistance. Thank you very much.
Thank you very much, Jorge. Now we're going to entertain some questions. We still have time. I actually have a question for you related to the method. In one of the slides, you say that it's not necessary to have enrichment of the culture. But I'm wondering if for pathogens like Listeria or Salmonella, E. coli, OH57, which are in very low numbers, if this method is applied or could be applied, or if you know something about it.
Yes, of course, we can use it. And the presentation, I said, like other methods like PCR, it requires at minimum a quantity of 1 million of bacteria in order to be accurately detected. However, with fish flow, we only need around 1,000 bacteria in order to detect it. So if in one sample we have a very few amount of it, we will easily be able to know that they are there.
I see. Do we have questions from here? Have you tried the fish flow technique for pathogens or just beneficial microbes?
For both, in the second research that I told and that I showed, it's also showed that we can detect the resistant genes for vancomycin, and this is a great alternative because if we receive normally in hospitals when we receive suspects for bacterial resistance, it will take around 1 day to take the results. However, if we perform this kind of assay in hospitals, we can take the result only in 2 hours. It's really saving time too.
Cool. Questions? Well, thank you so much for your presentation. And we will have a short break. We come back at 3 p.m. when Professor Bernadette Franco will present the Food Research Center for those interested. So we'll see you soon. Thank you.
Thank you very much.
Hello, everyone. For our last section today, we have Professor Bernadette Franco, who is our friend and also the coordinator of the Food Research Center. So she's going to be talking to us about the center and everything that is related to it. I guess it's very exciting. So let's hear from her.
All right. Hello, everyone. You are here. It's good. Don't sleep after lunch, please. And those who are watching us online, also don't sleep, please. Well, let me see. What? It's very easy, I know. Okay. The organizers of this winter school asked me to do a short presentation of the Food Research Center, which is, the nickname is Fork. I don't know if you know, but fork is a trick with the word fork, garfo, right? So this was an idea that a lot of people liked, some people disliked, but I like. The scientific director of FAPESP told me, que trocadilho horrível. I said, no, this is a very nice trocadilho, I like it. Well, for those who don't know, how do I move this? With this? No, this is, no. Ah, ok. Slide 1. Não tem aquele aparelhinho de mudar? Eu até tenho em casa. Bom, probably most of you don't know that Fork is what in São Paulo is called CEPID, Centro de Pesquisa, Inovação e Difusão, which is a program financed by FAPESP. In English, FAPESP calls this RDC, Research, Innovation, Diffusion, and Communication, something like that. So we started in 2013. After more than 2 years, we did the application in 2011. It took 2 years, so don't think you have problems with delays. They had 2 years to select these centers. If I'm not wrong, there were 99 applications in FAPESP and only 16 were approved. And we were very happy that one of those approved was our Food Research Center. So we started officially in 2013. And in last month, in 2024, the CEPID became what is called in the university CEPICS, which means that the center belongs to the university. It's not just a project anymore. You all know that FAPESP projects, they start one day, they finish day X. And our CEPID will finish next year, July 30, 2025. But the university made a very smart movement to put these centers. USP has 11 centers under its umbrella. So we are now a center that belongs to the university via Faculty of Pharmaceutical Sciences. So we are a center of the Faculty of Pharmaceutical Science and then hooked to the rectoria of our university, which is very good because with this we have some autonomy. We can look after money, we can do different things without the necessity to apply to FAPESP, to apply to CNPq, to apply to whatever we want to the industry. So we have some autonomy, which is very, very nice. If I can see this well here. So how big is this for? We are now 30 researchers. 30. We started with 21 and we were improving along the time, putting new people and eliminating other people that were not committed to the objectives of the center. So we did an arrangement in this almost 11 years. So now we are 30 professors. The last one integrated in the team is Slavi. And we are, from these 30 professors, 18 are from the Faculty of Pharmaceutical Sciences here. We have 3 professors from the Polytechnic School, Escola Politécnica. We have 1 professor from Public Health Institute, a Faculdade de Saúde Pública. We have 1 professor from the Faculty of Food Engineering and what's the other name? Animal Science, there, Engenharia de Zootecnia, Engenharia de Alimentos. We have 1 professor from the Faculty of Medicine, 1 professor from the Faculty of Agronomy in Piracicaba, and 1 professor in the Federal Institute of Minas Gerais. He's not from Sao Paulo, but he is also member of this team. We have also 2 professors of Unicamp, Faculty of Food Engineering. We have 1 professor from Instituto Mauá de Tecnologia, and we have 1 professor from Unesp, the Faculty of Medicine also. Huh? The other numbers are approximate numbers because you know better than me that these numbers change every day. Students come and go every day. So my last count showed us that we have approximately 18 postdoctoral researchers. We have approximately 80 master's and PhD students. And we have also the technicians that are in the labs and our project manager that you know well, which is Claudia, the one that solves all problems, administrative problems of the center. Well, the governance of the center is like this. I am the director of the center, as Uelinton said already. We have a vice director, which is Carmen Tadini from the Escola Politécnica. We have an executive director, which is Professor Eduardo Purgato, you all know him. We have our project manager, as I mentioned, Claudia, and we have an international advisory board. This international advisory board is I would say, fluidic. It changes with the time. When we started, we had, because this international advisory board has to do evaluations of the center every 3 years. So their role is very important because they look to our center with other eyes. So it's very important, and they made very good contributions along the existence of this center. And we have 3 divisions: the research division, which is our strongest part, then education and knowledge dissemination division, and the technology transfer division. Each one of these divisions has a coordinator and a vice coordinator. Come on. So we have an executive committee. I will not waste too much time with this. Não vai, eu estou tentando que não vai. Mas enfim. Porque eu tenho que mirar exatamente aqui. Eu tenho que ser boa de mira, que não é o meu caso. So we have an executive committee and we have I said we have a scientific committee. Let me see the first one. No. Here. The executive committee, we have a scientific committee. Who is the scientific committee? The most important. So the director, the vice director that I've already mentioned, the executive director, and we have, our center has 4 what we call pillars. I'll show you in a moment what's this. And the coordinators of these 4 pillars are also part of the scientific committee. Well, here are the 4 pillars. So our house rests, the roof sits on 4 pillars. The first one is systems biology food. Systems biology is food biochemistry, starting from the gene until the end product. All just a systemic approach, right? The second pillar is what we call food, nutrition, and health. So how the food components in things like this affect our human health. Focused only in humans. We don't work with animals. Okay, use the animals as models, but the objective is not for them, it's for humans, right? Then we have the third pillar, which is food's quality and safety, where microbiology comes, and the chemistry comes, where all these details on the food characteristics. And the fourth pillar is larger, but is effectively is the smallest one, which is on innovation and new technologies. This is the people from the engineering part, the technology part. So these are the four pillars of our center. And this arrow shows that the objective of the center, after 12 years that we are working, we achieved interesting results because the four pillars, they are intercommunicating. So what was done before the existence of this fork was the people of the biochemistry were the people of the biochemistry, the microbiology were microbiology, the engineers were the engineers. Now everything works together. So if you see the publications of our team, you have always people from different groups, not only from microbiology, not only from the food engineering, but people are interacting. And when I asked give an example of the best result of fork. I always say my best result is that we achieved to work together as a team. It's very difficult, particularly in an academic environment. And everybody thinks he's the only one, he's the best one, and right? So to work in teams is not easy. And we could do that very nicely. I think we get very good results. This is just showing what I just said. What happens with the fork? The science of producing the fork is outstanding. We have an H, you know that what's the H index? Everybody knows what's H index. So we have, the fork has a way to measure the scientific production. And we have a relatively high H index, which is 78. Right? As I said before, we have a synergistic activity. It's very important. And another thing that's very important is more than half of these 30 researchers have what we call Bolsa de Produtividade do CNPq, which is very difficult to get. You get these bursaries. It's an extra money every month for your pocket and for your lab, right? So this size is very small, but still gives a kind of recognition of your work. So it's not the money that matters, is the what it really means. It's very competitive, it's very difficult, right, Uelinton? Very difficult to get this bursary. And you know, we have Bolsa de Pesquisa level 1, 1A, B, and C. Yes, I think it's 4 and 2. So 5 levels. So we have, the professors have in different ranks, but still a very interesting result. Well, it's very difficult to highlight what are the main results in terms of science. I put some very few things here just for you to have an idea of what the fork works on. So detection, identification, and characterization of bioactive compounds. It's a very strong pillar. Actually, it's not a pillar, it's interpillar. It's a topic that's used also in the engineering people, in the people of system biology. So it goes from one pillar to the other. So these are actually projects, not the pillars. Oh, Jesus, what happened here? Cadê? Nossa, vocês trouxeram diferente. Ah, tela cheia lá. É essa, mano. So what are these bioactive compounds? Huge variety, right? So people here in our center work with detection, with the identification of these compounds, and the study of these compounds, characterization, what activity they have. The biosynthetic pathways in a systemic approach, as system biology, as I said. Evaluation of the activity of these bioactive compounds using all kinds of techniques. Omic techniques, preclinical and clinical studies, and also now cell models. Also, there are several people in the center that work with different types of cell models, 3D printing, 4D printing, right? There will be a very interesting course on 4D printing that one of our PhDs, our postdoc students is organized. If you are interested, I can give you more details later. Then another approach is also innovative applications of these food ingredients. As ingredients in foods, as components in special packagings, and all other things. Yeah? And also the use of byproducts of the food industry as other sources of nutrients for the humans and also for the microorganisms. We are working on an interesting project using food byproducts as nutrients for fermentation. And so you use the waste, it's a byproduct that you would throw away as a source of new, put in the circle again. So so what they call circular economy. The other highlight of the center is this Brazilian food composition table, which has a long story. It started in the faculty many years, well before the fork started, and fork absorbed this work, and it's the most important food composition table in the country. It started with Professor Lajolo in the years 70, 80, and it grew new information, and it's become very important. It's a database on the composition of foods from the Brazilian biodiversity. And so it's focused on the Brazilian foods, Brazilian fruits, Brazilian dishes, Brazilian preparations of meals, and what they call culinary preparations. And the interesting is that it's available on your cell phone. So the nutritionists, if you go to a nutritionist and you want to lose weight or you want to have some problem solved, she can use that app in the cell phone to prepare you a diet, which is very interesting, very useful. So a tool for evaluation of nutrients intake, energetic evaluation, and also diet planning, as I said. Interesting also is that most of the data in this database was originated here in our center. Not only in the center, but in works that were done before the center existed. So it's a huge, they have, I'm not sure about the numbers, but like 8,000 different types of foods. So it's very interesting. If you want, I can give you more details later on. It's a source of information for several epidemiological studies. In the like this one, the POF, o Programa de Orçamento Familiar, which is a Brazilian program organized by the IBGE, the Instituto Brasileiro de Geografia e Estatística, to see how people in Brazil are eating. What are they eating? Are they eating properly? Are they taking enough nutrients? Are they lacking what? So this POF is very important, and this table, the Brazilian composition table that was created here, is the reference for that. It's not only a reference, but it's part of the Brazilian food composition net. There's a net in the whole country. It's part of this. And also the Brazilian food composition table of our center is the model for what they are constructing now, which is a Latin American portal of food composition tables. So you probably know Christy, you probably know Eliana, you probably know Professor Eduardo. There are a lot of people working with this table. Next. Innovation and technologies. I had to highlight some few things. So obtention of plant extracts from the Brazilian biodiversity with antimicrobial, antioxidant, and several other things. So this extraction of these components of these plants, they have many applications. Another group is doing the encapsulation of these compounds in emulsions, nano-emulsions for applications in food, in biomaterials. And they are also, this is particularly the work done by the engineers, the Escola Politécnica da Engenharia de Alimentos in Pirassununga. They are doing this, designing these films, for not bacterial films, packing films, using these compounds for applications, for extending shelf life, for reducing oxidation, for different things. And now in food safety and quality, I could write a thousand of things, but I just put 3 just to show you a short idea. So microbial interactions in foods as strategies for improvement of their safety and their quality. Heard a lot about this week. The use of omics to understanding the microbial activity in food spoilage and food safety also. Also, you heard some of this here. And use of byproducts, so the food supply chain as sources of new nutrients for microbes in this what's called now fermentação de precisão, precision fermentation process. So you conduct your fermentation, you control your fermentation to get what you want. That's what it's called now precision fermentation. Very fancy. Well, now another part which is also important for this center is the part of education. We belong to a university, so we have to prepare the students. So we have, look at this, we have 6 different undergraduate courses involved in this center. Here, pharmaceutical science, the food science in Piracicaba, food engineering in Pirassununga, also in Unicamp, also in Instituto Manoel de Tecnologia. We have chemical engineering in Escola Politécnica, we have nutrition na Faculdade de Saúde Pública, and we have medicine na Faculdade de Medicina. And the postgraduate programs, masters and PhD, is even bigger. You may think that's strange, but we have one professor that works in the musculoskeletal system science, which is also related to how you eat, what you eat, how your muscles respond to your diet. Okay? And we have all those others, like food science here, food science and technology and food engineering again. So we have also microbiology, Instituto de Ciências Biomédicas. So we have students from different parts of this university. That's why the university wanted to have us belonging to the university, because we are really a net. What happened before was that food, there were groups working with foods in different parts of this university, in different cities, and we didn't talk to each other. So the people were doing the same things, or they were not doing complementary things that could be combined together. So this center will hopefully, has already, but will make it even stronger to make these people work together. Now, you are students, you must have known that we have this new PhD program. It's a postgraduate program in integrated systems in foods. You have already heard about that, right? So I will not give details on this, but I hope that João Paulo Fabi have convinced you that how important and how tricky was this step. Why is this so important for the students? Why is this so important for us? why is this so important for the university, and why is it so important for the country? Because we are the largest university in Latin America, you all know that. But we, as I said a few minutes ago, we had food science, food engineering, food nutrition spared all over the university. And we lost our strength with that because it was too scattered along the university. Now with the CEPICs, we can put all this together, and as you used to say, gente university que se cuide, porque we are coming, right? The good university, you have a very strong competitor here, okay? Probably João Paulo had shown this with this. I will skip this. Now I will go back to the other part, which is the knowledge dissemination. It's not the graduate and the postgraduate courses, and how we interact with the society, with other people, not our students. Okay, so we have these 4 websites that I just put here. You probably all know them, which were constructed to give information to the society in a level that the society can understand. It's not sophisticated, it's not ignorant, we are not influencers, we are not bloggers, we are giving science-based information in these 4 websites, right? Então, if you don't know, you have never visited one of them, I highly recommend to do that because it's very, very good. Thanks to works from Uelinton, from Eduardo, Eli, and Christy, they are doing this every day with the eyes open to keep these 4 websites always updated. Okay. The technology transfer. We have a few patents, not much. We should have more, but we have only a few. But we have several partnerships with several, not only industries, but organizations in the world. So here are the industries and the research projects that we have projects in combination, particularly the food and citrus is very so strong. Okay, so Braskem with the RTI and Nestlé and several others. And we have also collaboration with organizations, are not industries, but associations and the government. Então, em Anvisa, no Ministério da Agricultura, na Agriculture Ministry, in the Science and Technology Ministry, in all those societies that are mentioned there. Embrapa, we have a strong collaboration with Embrapa. Karina. She left. She was just here this morning, right? And international collaborations, I tried to make a complete list, but I gave up because it's a lot. It's a lot. Because FAPESP has this program of this BEPI, this bursary for the people that burst their scholarships to go out, to go to other countries. So all kinds of collaborations, all kinds of things. And not only that the students go there and come back. It's also projects that they are continued, so things that are made together. And we want to strengthen when the CEPICs really starts working. We want to make this stronger, so have these people working together. All right, and with that I finish. I hope this was a very short summary, and I just wanted to strengthen that it's really very important for us that we have these CEPICs now, and I want you invite you to make it even stronger. Okay? So thank you. If you have questions, no, you don't need to upload. No. If you have questions, I'll be pleased to answer. Not online, né? Sure.
My question is regarding the students that will do the master and PhD studies. So now they do with this new program, SIA, like very suspicious name. Sounds something
Pork with the C.
Yeah, but when they do the, let's say, PhD project with this program, so they automatically part of this fork system, or it's separate? How going to work? So they are part of the university, of course. They are part of the Faculty of Pharmaceutical Sciences, of course. They are part of the program, but they are part as well of fork.
Yes. Yes. Look, I said in the beginning that we are 30 professors in the CEPID. Now, CEPIX has to be something from USP, so I have to cut all the people that are not from USP. But I want also, I think we should do what? We do a cleaning. There are several professors of USP that are not so committed to the center. In the counterpart, we have a lot of others that are dreaming of being part. I could not, they asked me to be part of the CEPID during this 12 years, and I had to say no, because I said the money is only one. If I have to divide the money for in 30 is one thing. If I divide for 60, it's the money is short. It would be even shorter, so no way. But now, we can work in a different way. We can put the people, we can be more selective to have exactly those that veste a camisa, as we say, who go after money, who innovate, who are involved in teaching, who are doing good science. So we can be more selective. It's a very difficult attitude from the coordinator. I'm glad that I will retire next year. But the next coordinator will have to be very political to do this, because we had the FAPESP as a, I would say, excuse to say, no, I don't want you because the money. Now we don't have this money. So what would be the reason to say somebody that we don't want you? Yeah? So it will be, you have to sit down and write our regimento, what they say, né? We are in this step, because this CEPIX was approved less than 1 month ago. What day is today? It was on 27th of June, less than 1 month. So we didn't have time. Things are not so quick. So we will have to be very careful preparing the bylaws of this center, because we have to be very high standard oriented in everything, in teaching, in researching, in getting money, in innovation. So it will be not an easy task, but we have to start somewhere, right? Okay. So the students are with the professors. So in CEPID, we had to use money of CEPID to take you to a congress. I had to register you in the FAPESP web system, indicating that I'm using FAPESP money to pay somebody that belongs to the team. Now I will not have to do that. So that may make things easier or not. You will see. Okay.
Hello, Professor. Is there any opening for the postdoc, maybe apart from masters and the PhD?
Sorry, I don't hear you well.
Is there any opening for the postdoc, apart from masters and the PhD student?
Jesus, I don't understand you. Of course, postdocs. Of course, they are more than welcome. We have several postdocs. Look, it depends more on the professor than on the center. I will not tell you, no, you are not, you will not be a postdoc. It's not me. It's not me that will say that. It's your supervisor. Oh, I have a good candidate. So, but what happens now is that we had in this center that we had before from FAPESP, we had the scholarships from FAPESP. Now we don't have any scholarship. So your supervisor will have to look after the scholarship for the PhD or for the postdoc or for the scientific initiation. It's now each professor will have to go after the funds. So the pink times are gone.
Then what about the student if he need to come for interns, like internship?
Gente, não escuto, não entendo. Well, our arms are open to every good student. So, okay. Yes, the student has to contact one of the professors and do the negotiation like everywhere in the world, right? You can, the person who is interested can write to the director, and then the director will send him, no, your area is such and such and such, so you can contact the professor A, B, C, and D. Okay? What did you say?
And then I redirect to somebody.
No, not always. I receive all kinds of things. I direct to Uelinton, I direct to you, I direct to Ramon, I direct to João Paulo Fabi, I direct to different people. Depends on what the students want to do. Sometimes the student doesn't know what he wants, and then it's a little bit more difficult. But
so I have a question that maybe I know the answer, but maybe they don't. So now that it's like PORC or in the other CPDs are under USP, what is USP giving in return to the centers? So they, what is the advantage?
Two things. One is that they promised, it's 99% sure that we will receive a new técnico especializado de nível superior. The one technician for the laboratory in the fork, which is for to do the work that Miriam is doing. Miriam is the technician there. So Miriam is paid by the FAPESP money. FAPESP money, entre aspas, more or less, because I cannot use FAPESP money to pay people. But the money that comes that we make in the center by the private projects that we have, we pay Miriam. If they give us the technician, I will not have to pay her anymore. And the second thing is that we are now an organized society in the university. So if you apply to a project, to a thematic, or to a INCT, or to a Embrapi, or whatever, where you can get money, you are not a bunch of professors that are inventing something. You are something that belongs to the university. It's a center. You have the shelter of the university, which is important. As far as I heard from FAPESP, it's very important. The president of FAPESP now was our rector, Professor Zago, and he said that everything that comes to FAPESP that is under this umbrella of the TPICs will have a different look. Will be, I don't know how different. It will be more rigorous or less rigorous. I don't know. Anyway, it's a kind of a grief. Eh? It's more powerful. But if you are more powerful, you have more responsibility, right? And so you have to be very careful.
Great power comes great responsibility.
Great power. Except in Brasilia, but that's another thing. Okay. So you are all welcome. Those who are listening online also, if you want to contact, there is the website is very easy to find. Food Research Center USP, you can find everything.
Yeah.
Okay.
Great. Thank you so much.
Thank you.
Oh, I'm not appearing in the TV. And with that, we end the day, and we come back tomorrow in the same time. So see you guys tomorrow. Thank you very much.